What lies beyond Neptune? Neptune is the last officially recognized giant planet in the solar system, but it is not the end. Crossing its orbit, we enter a region called the Kuiper Belt, home to thousands of icy bodies, many of them larger than asteroids and with highly unconventional orbits. This area is so dim and vast that telescopes can only observe a tiny fraction of what is out there. What is known is that it houses a complex collection of objects that shouldn't be there, or at least not in the way they are. Among these objects are names like Pluto, Eris, Makemake, and Haumea, all classified as dwarf planets, but there are others like Sedna and 2012 VP113 with orbits so distant and elongated that they seem to come from another system. Sedna, for example, never gets close to the Sun. It spends nearly its entire orbit near what would be the solar system's gravitational boundary. That alone is strange. What pushed it there? Some of these objects not only have distant orbits, but they also share similar points of closest approach around the Sun, a pattern that is unexpected and highly unlikely to occur by chance. This kind of astronomical coincidence suggests they are being influenced by something massive that we have not yet detected. This anomaly is one of the reasons behind the hypothesis of the existence of Planet 9. The theory of Planet 9 emerged based on simulations that attempted to explain the orbital distribution of Kuiper Belt objects. For these patterns to make sense, a body with at least 5 to 10 times the mass of Earth would have to be exerting gravitational influence. This planet would be 10 to 20 times farther than Neptune and would complete an orbit every 10,000 to 20,000 years, but so far, no one has been able to observe it directly. If this planet exists, it would be in such a dark and cold zone that it does not reflect enough light to be seen with current telescopes. Detecting it requires patience, long-term data, and analysis of the orbital movement of hundreds of smaller objects. It's like inferring the presence of an elephant walking in the dark by observing leaves rustling in the forest. Even so, the traces are there, and they are accumulating. Beyond Planet 9, some suggest there may be multiple massive bodies beyond Neptune. In 2021, a group of astronomers proposed that some orbits might be affected by small, scattered planets instead of a single giant. Other scientists go further. They suggest that part of this region was influenced by a star that passed close to the Sun billions of years ago, disrupting everything. Another intriguing point. Many of these objects have strange inclinations relative to the plane of the solar system, as if something had pushed them out of more regular orbits. This raises suspicions of cataclysmic events in the past or even ongoing external perturbations. And with each new object discovered with atypical behavior, the mystery deepens. Telescopes like Subaru in Hawaii and the Vera C. Rubin Observatory, expected in 2025, are the main bets for hunting these hidden bodies. They can map vast areas of the sky in high resolution, detecting slowly moving objects. Each new discovery helps build the gravitational map of the solar outskirts, and that map, so far, does not match the standard theory. The most impressive part is that even with all current technology, we know only 0.01% of the estimated objects beyond Neptune. Most are invisible, spinning in absolute cold, emitting no light or heat. It's an entire universe within our own system that we have yet to explore. And what has already been discovered is enough to change established models of planetary formation. Moreover, the very existence of the Kuiper Belt challenges the theory of the solar system's formation. According to classical models, the material density there should be much lower. This means that the planets may not have formed exactly where they are today. They may have migrated to their current positions, scattering or capturing objects along the way. And finally, studying what lies beyond Neptune isn't just about planets. It's about understanding the limits of solar gravity, the remnants of ancient collisions, echoes of disturbances from other star systems, and even traces of interstellar objects. This frontier is alive, active, and constantly evolving, and we've only just begun to understand it. The secrets at the edge of our solar system. The solar system has different boundaries depending on what you measure. The most common is the heliopause, which marks the end of the influence of the solar wind. This barrier was crossed by the Voyager 1 and 2 probes, and the data they sent back was surprising. Outside the heliosphere, the density of the interstellar medium was greater than expected, and the magnetic fields behaved in completely unexpected ways. In other words, we don't even really know what the outside is like. But before reaching the heliopause, there is a complex zone called the trans-Neptunian region, which includes the Kuiper belt and extends to the hypothetical Oort cloud. It is in this region that the greatest discrepancies with current astronomical models occur. Objects there behave as if they obey their own rules, and no one knows exactly why. Some don't even orbit in the same plane as the planets. For example, the Voyager 1 probe observed an abrupt drop in solar particles when it crossed the heliopause, as expected. But instead of a smooth, uniform magnetic field, it found an unstable structure full of turbulence. This indicates that interstellar space is much more active and chaotic than older models suggested. And this chaos begins right at the edges of our own system. The behavior of long-period comets is also a mystery. Some of them appear out of what seems like nowhere, coming from regions far beyond the Kuiper belt with extremely high inclinations and unstable orbits. This suggests that the Oort cloud really exists, a spherical shell of frozen bodies, possibly containing trillions of comets orbiting the Sun up to a light-year away. But to this day, no object has been directly observed in that cloud. Another piece of evidence that the edge of the solar system hides something important is the existence of objects with almost intergalactic orbits. Sedna, for instance, never really approaches the Sun. The question is, how could such a body have formed there? The most accepted hypothesis is that external forces, perhaps a star that passed nearby billions of years ago, pulled Sedna and other objects into these extreme orbits. Moreover, the amount of mass in the Kuiper belt is greater than previously thought. This contradicts the planetary formation disk model, which predicts that most of the mass should have been absorbed by the giant planets. What is seen, however, is a surprising concentration of objects with disturbed orbits. This may indicate that the solar system has undergone major mass redistributions over time, perhaps even due to interactions with other systems. The geometry of these orbits is also intriguing. Many objects have steep inclinations relative to the plane in which the planets orbit. Some revolve almost perpendicularly to the solar disk. Others are grouped in specific regions of the sky, as if guided by something. This suggests an invisible pattern, possibly caused by one or more massive bodies not yet detected. Another curious fact: simulations made to explain the behavior of these objects require not only the presence of Planet 9, but also a history of planetary migration. This means that Jupiter, Saturn, Uranus, and Neptune may not have formed where they are today. They would have moved, sculpting the solar system in their path. This idea is reinforced by models like the NICE model, which simulate these migrations with impressively consistent results. The heliopause is also not a fixed line. It moves according to the solar activity cycle. In periods of higher particle emission, the heliosphere expands. When the Sun is calm, it contracts. This means the size of the solar system changes constantly, which further complicates our understanding of its real boundaries. Outside the heliosphere, interstellar particles begin to dominate. But data from the Voyagers indicate there is a kind of dampening zone where the particles mix, creating a turbulent transition full of magnetic interactions. This intermediate zone had never been predicted in detail and is now considered one of the most dynamic places in the solar system. This complexity shows that the boundary of the solar system is not a calm, frozen place as once imagined. On the contrary, it is active, energetic, and full of disturbances. Each new discovery forces astronomers to revise old theories, many of which had been accepted for decades. It is there, at the edge, that space science meets its greatest challenges. And the most impressive part is that all this is within our own system. We're not talking about another galaxy or a distant black hole. We're talking about a region that begins just beyond Neptune, a territory that, despite being part of what we call the solar system, we still don't truly understand. And that's exactly why it remains so fascinating and so full of secrets. This region of the solar system doesn't make sense to scientists. When mapping the orbits of objects beyond Neptune, astronomers noticed something strange. They are not randomly distributed, as would be expected. Many of these objects, especially the more distant ones, share similar patterns, as if something were organizing their paths. This invisible organization cannot be explained by Neptune or the known planets. It's like finding a trail in the forest without seeing who made it. One of the greatest enigmas is the so-called orbital clustering. Some bodies share the same perihelion point, the closest point to the Sun, and this alignment persists even after millions of years of simulation. The chances of this happening by accident are extremely low. This anomaly is one of the main pieces of evidence supporting Planet 9 or some other type of unknown gravitational influence. In 2016, astronomers Konstantin Batygin and Mike Brown published a study modeling this clustering. They showed that the best explanation for the data would be a hidden planet, several times more massive than Earth, orbiting more than 500 astronomical units from the Sun. The scientific community was divided. Some saw the study as a revolution, others called for caution. But the common point was this: something there doesn't make sense. The difficulty increases when considering the orbital period of these objects. Many of them take thousands or tens of thousands of years to complete a single orbit around the Sun. That means we are only observing a tiny fraction of their trajectories. Orbit analysis is done with incomplete data, which makes the models even more uncertain. Even so, the patterns persist. Another factor that complicates everything is orbital inclination. Many of these objects do not follow the plane of the solar system, as would be expected if they had formed alongside the planets. Instead, they orbit at highly inclined angles, some reaching 40 degrees or more. This is nearly impossible to explain with standard formation models. Some force must have altered these angles after their formation. And it's not just about orbits. The very composition of these bodies raises questions. Some dwarf planets like Haumea spin so rapidly that they are flattened. Others, like Arrokoth, have a peanut shape, indicating they didn't experience violent collisions, which contradicts what was expected for such a populated region. In other words, the physics of these bodies is strange, both in behavior and in origin. There's also the mystery of mass distribution. The Kuiper belt should contain much more material than we observe. Original models predicted it would have a mass hundreds of times greater. But today, even with thousands of cataloged objects, the total doesn't exceed a fraction of that. This raises hypotheses. Perhaps some of the material was ejected into the Oort cloud or absorbed by rogue planets we've never seen. The theory of planetary migration tries to explain some of these anomalies. According to it, Jupiter and Saturn moved inward and outward in their early millions of years, pulling and pushing debris like a giant gravitational plow. This movement would have launched objects to the solar system's edges, generating chaotic orbits. But even this model doesn't fully explain the current organization of the most distant bodies. A baffling example is the object 2008 KV-42, also known as DRAC. It orbits the Sun in a retrograde manner, that is, in the opposite direction of the planets. This is extremely unusual and hard to justify. How could an object acquire such an eccentric orbit without escaping the sun's pull? This reinforces suspicions of external, possibly even interstellar influences, shaping the outer edges of the solar system. And then there's the numbers issue. Simulations predict that there are over 100,000 objects larger than 100 kilometers in diameter beyond Neptune. But we know of only about 3,000. That's a tiny fraction, and it means that most of the data we use to build models comes from an extremely limited sample. The unknown is not just vast, it's the norm in this region. Even the most advanced technologies struggle to directly observe these bodies. They reflect very little sunlight and move slowly. Finding them requires repeated observations over years and algorithms capable of detecting nearly imperceptible movements. But the more we observe, the more exceptions we find, and the patterns that emerge challenge known rules of astrophysics. Today, scientists have models, but they also have a problem. Reality isn't following the predictions. When that happens in science, there are two paths. Either the data is wrong or the model needs to change. In this case, the data keeps piling up, pointing to a region that challenges our most basic assumptions about how the solar system should work. And the model, for now, is creaking. The solar system may be much larger than we imagined. For decades, it was believed that the solar system ended near Neptune or Pluto. That view changed with the discovery of the heliosphere, the Oort cloud, and extreme objects. Today, some astronomers work with the idea that the true size of the solar system may extend to twice the distance between the Sun and the nearest star. That is, up to 100,000 astronomical units. That's more than 1 light-year in radius. What defines this limit is not a physical point, but the gravitational influence of the Sun. As long as a body remains bound to the Sun's gravitational field, technically, it is part of the solar system. This includes, for example, comets from the Oort cloud, which orbit so slowly that a complete cycle may take millions of years. These bodies are so far away that the Sun is just a bright star in their sky. The existence of the Oort cloud has never been confirmed by direct observation, but it is accepted by most astronomers because it explains the origin of long-period comets. These comets come from all possible angles, not just from the plane of the solar system. That suggests a spherical distribution of distant objects, and if this cloud really exists, it may contain up to trillions of frozen bodies. A surprising point is that, in simulations, the Oort cloud appears to be unstable over the long term. Small disturbances, like the gravitational field of a nearby passing star, or even the galactic tide of the Milky Way, can push comets into the solar system. This means the solar system is affected by events happening far beyond it, on an almost galactic scale. Stars don't stand still. The Sun travels through the galaxy and occasionally passes near other stars. Models show that in the past 10 million years, at least 20 stars may have come close enough to disturb the Oort cloud. In some of these passes, comets may have been launched into the inner solar system or even ejected into interstellar space. Furthermore, there is the possibility that the Sun was born in a stellar cluster, where the star density was much higher. If true, the early solar system was far more chaotic than imagined. Collisions, exchanges of material, and gravitational captures would have been common. It is possible that the Oort cloud is, in part, made up of objects that didn't even form with the Sun, alien bodies incorporated into its gravity. What this suggests is that the solar system may be an open system, constantly exchanging with the galactic environment. And if it captured external objects in the past, it may still be doing so today. The discovery of interstellar objects like Oumuamua and Borisov, which passed through the solar system, reinforces the idea that space between stars is far from empty. If the solar system extends to the Oort cloud, or beyond, then we are only just beginning to explore it. The Voyager and New Horizons probes are still within this structure, and their data shows that the Sun's influence remains active even in regions once considered outside. The transition between the solar system and interstellar space isn't a sharp boundary, it's a gradient of interactions. The heliosphere itself, the bubble created by the solar wind, is just an inner layer of this boundary. It changes shape as the Sun moves, like a bubble being pushed by the galactic wind. And surprisingly, simulations show it may have a tail, similar to a comet's, extending for thousands of astronomical units. This adds an extra layer of complexity to the notion of where the system ends. Meanwhile, gravitational boundaries are more enduring. Even at this absurd distance, the Sun still holds bodies in extremely slow orbits. That's one of the reasons why the concept of the boundary of the solar system is being redefined. Instead of a circle around the Sun, the solar system may be seen as a layered structure that extends as far as the Sun can maintain its influence. But the farther we look, the harder it gets to detect. Oort cloud objects are small, cold, and incredibly slow. They emit almost no light and reflect very little. Detecting them would require technologies not yet available, or at least extremely long and patient observations. For now, this is an almost theoretical region, but the evidence is piling up. And even among astronomers, some believe that the real solar system could be even larger than the Oort cloud suggests. Some models predict that objects that once belonged to it have already been flung into interstellar space, forming a debris halo that silently surrounds us. That could mean we're living at the center of a structure we haven't yet fully seen. The strange dance of trans-Neptunian objects. Beyond Neptune, dozens of celestial bodies follow orbits that seem to obey an invisible logic. These are known as trans-Neptunian objects, or TNOs, and they behave in ways that contradict the expected norms of orbital mechanics. Many have elongated, tilted, or even retrograde orbits, as if something unseen is nudging them. It's as if these objects are following a cosmic choreography we don't yet understand, and something might be conducting the dance. One of the most puzzling features is gravitational resonance, where objects synchronize their orbits in a repeating pattern that avoids collisions. This doesn't happen by chance. It usually requires an external gravitational force to lock bodies into rhythm. And many TNOs, even those far apart, seem to show this synchronized behavior. That coordination hints at a hidden influence pulling the strings from afar. Even more mysterious is the orbital clustering. Several TNOs have similar perihelion directions and orbital tilts, a statistical anomaly that's incredibly unlikely to happen randomly. Their orbits are aligned in space in a way that defies expectations from random distribution. This clustering is one of the main pillars behind the hypothesis of a Planet 9, or possibly more than one massive body. Some TNOs, like 2015 TG387, never come close enough to the known planets to be affected by their gravity. And yet they maintain strangely ordered trajectories. These orbits can only be explained by the influence of something much farther out, something massive, cold, and invisible to current instruments. It's as if they're being shepherded by a ghost planet. There's also the question of extreme orbital inclinations. Objects like Niku and Drac orbit at steep angles, nearly perpendicular to the planetary plane. Such high-inclination orbits are hard to explain under standard planetary formation models. One possibility is interaction with a distant planet outside the solar system's plane. Another is influence from larger-scale forces like galactic tides. Some TNOs are categorized as detached objects because they never come close enough to interact with Neptune or the gas giants. Their orbits exist in gravitational isolation, It's as if they were placed in their current paths by an external force and then abandoned there. Standard solar models can't account for this, but simulations that include a distant undiscovered planet do. In fact, computer models show that the behavior of these orbits only makes sense if we add a super-Earth-sized planet orbiting far beyond Neptune. When such a planet is included in the simulation, the weird orbits start lining up logically. Without it, the orbits remain chaotic. It's as if nature is hinting at a missing piece in the puzzle. In 2023, a study revisited the 17 most extreme TNOs and confirmed their orbits maintain alignment over tens of thousands of years. That stability is hard to explain without a massive, consistent gravitational influence. More telling is that even when Neptune is removed from simulations, the alignment persists. Whatever is causing it must be much farther and heavier than Neptune. This disrupts the idea that the solar system is a calm, predictable structure. Instead, the outer regions appeared to be a mix of order and instability shaped by forces we still don't fully understand. Some may be relics of ancient events, others could be signs of ongoing gravitational tug-of-war. The outer solar system is not quiet, it's active and unsettled. The orbits also raise questions about how and where these objects formed. Did they originate in place, or were they thrown outward by planetary migration or even interactions with other star systems? Their current movements may be the result of billions of years of cosmic shuffling. Each TNO could be a leftover from a different chapter in the solar system's evolution. Despite strong indirect evidence, Planet 9, or whatever force is shaping these orbits, remains undetected. Yet, with every newly discovered object showing odd trajectories or shared orbital features, the pattern gets harder to ignore. It's like hearing the rhythm of music without seeing the musician. We know something is there. We just haven't found it yet. This is not speculation. The orbital patterns are statistically solid and backed by observational data. Astronomers are increasingly confident that something massive is affecting these distant objects. What that something is remains open, but it's clear the outer solar system is hiding something significant. Sedna, the orphan planet with an impossible orbit, is one of the strangest bodies ever found in our solar system. It takes about 11,400 years to complete a single orbit around the Sun, over 40 times longer than Pluto. But what really sets it apart is where it orbits. Sedna never comes close enough to the planets to be influenced by them, nor far enough to be entirely outside the Sun's reach. It sits in a gravitational no-man's land. Discovered in 2003, Sedna is roughly 1,000 kilometers across, making it a dwarf planet. But its orbit is what caught astronomers off guard. Its closest point to the Sun, perihelion, is 76 astronomical units, nearly double Pluto's average distance. Its farthest point, aphelion, is an astonishing 940 AU. No existing model of solar system formation predicts such an orbit. Sedna's isolation is its most perplexing trait. It doesn't interact with Neptune, it's untouched by Jupiter, it follows a path that seems completely disconnected from the gravitational influence of known planets. This makes it hard to explain how Sedna ended up where it is. Standard formation theories break down in this region. Something else had to shape its orbit. One idea is that Sedna was disturbed by a passing star in the early days of the solar system. If a star moved close enough, within a few hundred AU, it could have pulled Sedna into this eccentric orbit. That would mean the solar system was born in a dense stellar nursery filled with close encounters and gravitational chaos. Another possibility is that Sedna wasn't born here at all. It may be a captured object, pulled from another solar system during a stellar flyby. If true, Sedna could be the first alien world we've found orbiting our own star. Its composition in orbit would then offer clues not only about our history, but about the history of another system entirely. Sedna might also be the first concrete piece of evidence for Planet 9. When simulations include a massive, distant planet, 5 to 10 times the size of Earth, Sedna's orbit suddenly makes sense. In fact, it becomes expected. That planet would act like a shepherd, stabilizing bodies like Sedna into these strange, stretched-out paths over time. What's even more intriguing is that Sedna is not alone. Objects like 2012 VP-113, Lelea Cunahuna, and 2010 GB-174 have similar orbital behavior, high perihelion distances, and no significant planetary interactions. They belong to a class now known as sednoids. The fact that multiple objects follow this pattern suggests a shared gravitational origin. Sedna is also incredibly cold, likely among the coldest bodies in the entire solar system. Its surface temperature is estimated to be around -240 degrees Celsius. That makes it a time capsule, preserving original materials from the early solar system. Studying Sedna could reveal organic molecules or ices untouched for billions of years. But getting there is a major challenge. It's so far away that even our fastest spacecraft would take decades to reach it. A mission to Sedna would require cutting-edge propulsion systems or gravity assists from planets like Jupiter. There have been proposals, including missions using electric propulsion or advanced nuclear engines, but none have left the planning stage. For now, Sedna remains out of reach. Understanding Sedna means understanding the solar system's birth environment. If it was pulled into place by a passing star, it implies a crowded early history. If it was captured, it points to interstellar exchanges of matter, something once thought unlikely. Either way, Sedna is a fossil of a time we know almost nothing about. The more sednoids we find, the more urgent the questions become. Are we seeing the result of a massive object shaping their paths, or the echoes of a chaotic past where our sun brushed against others? Sedna is not just a curiosity, it's a clue, and maybe even a warning that the architecture of the solar system is far more complex than we imagined. There is no consensus on where Sedna came from or what shaped its orbit, but one thing is clear. It doesn't belong to any category we previously recognized, whether it's a captured world, a survivor of early chaos, or a planet guided by an unseen force. Sedna forces us to rethink everything we thought we knew about our own cosmic neighborhood. The Oort cloud, a nearly mythical boundary. The Oort cloud is one of the most intriguing and most elusive structures ever proposed in astronomy. It's a theoretical shell of icy objects that may surround the solar system at a distance of up to 100,000 astronomical units from the Sun. That's nearly a full light-year away. No object has ever been directly observed in this region, and yet the Oort cloud remains a widely accepted idea. Why? The strongest evidence for its existence comes from long-period comets, those that appear from seemingly random directions and take tens of thousands of years to return. These comets don't originate from the Kuiper belt, which is disc-shaped and lies within 50 AU. Instead, their trajectories suggest a vast spherical reservoir of icy bodies surrounding the solar system in all directions. That's what the Oort cloud would be. It's thought to contain trillions of icy objects, many no bigger than mountains, but possibly including bodies the size of planets. These objects are believed to be loosely bound to the Sun, making them highly sensitive to outside forces, like passing stars or gravitational tides from the Milky Way. Even a slight disturbance could send one falling inward toward the Sun as a comet. No telescope has ever seen an Oort cloud object. They're too distant, too small, and too dim. But statistical analyses of comet trajectories continues to suggest a remote origin point, far beyond the Kuiper belt. It's the only explanation that fits the data. Still, without direct observation, the Oort cloud remains a theoretical boundary, one that's difficult to confirm but hard to reject. Some models suggest the Oort cloud might be layered, with an inner and outer region. The inner Oort cloud, also called the Hills cloud, could begin around 2000 AU. The outer layer might stretch to 100,000 AU. Objects in the outer layer would orbit so slowly that a single revolution could take millions of years. These are some of the slowest moving bodies in the known universe. The origin of the Oort cloud is still debated. One theory is that the objects were ejected from the inner solar system during the formation of the gas giants. As Jupiter and Saturn migrated, they flung ice-rich debris outward. Most escaped into interstellar space, but some got caught in long elliptical orbits and eventually formed the Oort cloud. If true, it's a relic of planetary chaos. Another hypothesis suggests the Oort cloud isn't purely homegrown. During the early solar system's life, the Sun may have passed near other stars, possibly stealing some of their outer debris. That means the Oort cloud might contain interstellar immigrants, bodies that didn't form around our Sun but now quietly orbit it from immense distances. Because of its distance and distribution, the Oort cloud may not even be a sharply defined cloud. It might be more like a diffuse halo, a gradient of icy debris that becomes less dense the farther you go. This makes it even harder to study, since any sharp boundary we imagine may simply not exist. It could fade into interstellar space seamlessly. The Oort cloud may also help explain mass extinction events. Some researchers have proposed that periodic disturbances, like a passing star or gravitational waves from the galaxy, could send swarms of comets toward the inner solar system. One impact theory even involves a hypothetical companion star, nicknamed Nemesis, that could disturb the Oort cloud every 26 million years. In 2019, the interstellar comet 2I Borisov entered the solar system. Its trajectory showed it came from outside, perhaps from someone else's version of an Oort cloud. This suggests that Oort-like structures could be common features of stellar systems. If every star has its own cloud of icy debris, the interstellar medium might be full of rogue comets traveling in and out of alien systems. Efforts to detect the Oort cloud directly continue. Future infrared space telescopes or even dedicated long-range probes could one day detect its outermost members. Until then, our understanding remains indirect, built from the arcs of comets and the gaps in our models. It's like mapping a forest by watching the occasional falling leaf. The Oort cloud may be real, or it may need to be redefined entirely. But if it does exist, it's the true edge of the Sun's influence, and a reminder that our solar system isn't a tidy neighborhood. It's a dynamic, layered structure, still shrouded in darkness. And somewhere out there, in that near-mythical space, the next surprise may already be on its way.
The Kuiper belt and its mysterious bodies. Just beyond Neptune lies the Kuiper belt, a wide ring of icy debris and planetary remnants. For years it was overlooked. Most people thought Pluto was alone in its distant orbit. But today we know it's just one of thousands of bodies in this frigid zone. Some are as small as asteroids, others rival Pluto in size, and many of them are orbiting in ways that don't quite make sense. The Kuiper Belt begins around 30 AU from the Sun and stretches to about 50 AU, although some models extend it farther. It contains objects known as KBOs, Kuiper Belt objects, and they vary dramatically. Some are in circular orbits, others are stretched, tilted, or even retrograde. These patterns hint at past gravitational upheaval. Something disturbed this region early in the solar system's history. One of the oddest discoveries in the Kuiper Belt was Haumea, a fast-spinning object shaped more like a rugby ball than a sphere. It also has a ring and at least 2 moons. Haumea is part of a family of objects believed to be fragments of a violent collision, possibly the only known case of a disrupted planet in the Kuiper Belt. Its rotation period is under 4 hours, dangerously close to breakup speed. Another major player is Eris, slightly smaller than Pluto but more massive. Its discovery in 2005 was a turning point. It's what led astronomers to reclassify Pluto as a dwarf planet. Eris orbits far beyond Pluto in a highly elliptical path. It also has a moon, Dysnomia, and a surface rich in frozen nitrogen and methane, much like Pluto, but colder and more reflective. Then there's Makemake, a reddish, methane-covered world with at least 1 moon. Its orbit is slightly inclined, making it part of a subset of KBOs that seem to avoid the gravitational influence of Neptune. These detached objects follow paths that don't align with standard orbital evolution. Their existence implies either an ancient disturbance or a hidden influence still active today. The Kuiper Belt is also full of resonant objects, like Plutinos, which are locked into a 3-to-2 orbital resonance with Neptune. That means they orbit the Sun 3 times for every 2 Neptune orbits, a configuration that keeps them from ever colliding. This kind of gravitational choreography indicates a past in which Neptune likely migrated outward, sweeping objects into new positions as it moved. Migration theory explains much of the belt's current state. As Neptune and Uranus shifted during the early days of the solar system, they dragged icy bodies along with them, creating pockets of stability and chaos. Some objects were pushed into the Kuiper Belt, others were thrown into the Oort cloud or ejected entirely. What remains is a fragmented fossil record of those migrations. Many KBOs rotate unusually slowly, or, in some cases, in chaotic, tumbling motions. Their surfaces are often red or gray, possibly from irradiated organics or space weathering. Some show signs of cryovolcanism or internal oceans. These are not just frozen rocks. Some may still be geologically active, driven by radioactive decay or tidal forces from small moons. The discovery of Arrokoth in 2014 and its flyby by New Horizons in 2019 revealed an untouched primordial object. Arrokoth is composed of 2 lobes gently merged together, indicating it formed slowly in a low-collision environment. This challenges previous views of a violent early solar system. At least in the Kuiper Belt, some parts were surprisingly calm. Despite all this, we've likely discovered less than 1% of the Kuiper Belt's total population. The majority of objects are too small, too faint, or move too slowly across the sky to be easily detected. New surveys, like those planned by the Vera C. Rubin Observatory, may uncover thousands more, including candidates for new dwarf planets. The Kuiper Belt is also part of a bigger puzzle. As we study more KBOs, we may also uncover more clues about our own origins. The frozen archives of the Kuiper Belt could hold the secrets of the early solar system and the very conditions that led to life as we know it.
Why Pluto is only the beginning. For most of the 20th century, Pluto was seen as the mysterious 9th planet at the edge of the solar system. But that perception started to unravel with the discovery of other icy bodies beyond Neptune. By the early 2000s, it became clear that Pluto was not alone, just one member of a much larger family. That family lives in the Kuiper Belt, and it contains objects that rival Pluto in size and complexity. When Eris was discovered in 2005, it immediately challenged Pluto's uniqueness. Eris was slightly smaller in diameter, but more massive, and orbiting even farther from the Sun. Its existence raised an uncomfortable question. If Pluto was a planet, why not Eris too? Rather than add a 10th planet, astronomers redefined what a planet is, and Pluto was reclassified as a dwarf planet. But that debate obscured something more important: the realization that Pluto was just the tip of the iceberg. Since then, dozens of other dwarf planets and large Kuiper Belt objects, KBOs, have been found, including Haumea, Makemake, Gonggong, and Quar. Many of them have moons, some have atmospheres, and a few may even have subsurface oceans. Pluto itself surprised everyone when the New Horizons spacecraft flew past it in 2015. Instead of a frozen, dead rock, Pluto revealed a dynamic surface with glaciers, mountain ranges, and signs of geological activity. Its heart-shaped plain, Sputnik Planidia, may even be the site of an ancient impact. The presence of a possible liquid ocean beneath the ice suggests that Pluto, and perhaps others like it, are not geologically dead. Other KBOs have features just as unusual. Haumea rotates so fast that it has an elongated, football-like shape. It's also surrounded by a ring, making it one of the only known ringed objects beyond the giant planets. Quar also has a ring, and that ring is located outside its Roche limit, where traditional physics says it shouldn't exist. These objects are rewriting the rules of what's possible in the outer solar system. What's more, Pluto and his kin offer insight into the early chemistry of the solar system. Their surfaces are rich in volatile ices, like methane and nitrogen, as well as organic compounds. Some even show evidence of complex molecules like tholins, which form when solar radiation alters organic material. These may be precursors to life, preserved in deep freeze for billions of years. The Kuiper Belt is also home to binaries, pairs of objects that orbit each other closely. Pluto and its moon Charon are the most famous example, but other binary systems exist among smaller KBOs. These pairs may have formed during gentle mergers in the early solar system, offering clues about how gravity shaped small bodies before the age of planets. One of the key takeaways from Pluto's story is that planetary classification misses the point. Whether you call them dwarf planets or planetesimals, these objects are active, diverse, and scientifically rich. They don't fit neatly into our old categories. And the more we discover, the more it seems that the solar system's architecture is far more complex than a simple Sun plus 8 planets model. Some scientists argue that Pluto should never have been called a planet, not because it's too small, but because it was never alone. From that perspective, the solar system has always had a third zone, not just rocky planets and gas giants, but also a population of icy worlds orbiting in the deep cold. Pluto was simply the first one we saw. Exploration is just beginning. Missions like New Horizons and future telescopes like the James Webb Telescope and Vera C. Rubin Observatory are expected to reveal hundreds of new distant objects in the coming years. Many of these may be planet-sized, and some could even have atmospheres or internal oceans. Pluto was not the end, it was a door. With each new discovery, the line between planet, moon, and asteroid gets blurrier. The outer solar system is a realm of hybrids, oddities, and exceptions. And perhaps that's the real lesson of Pluto, that the solar system didn't stop where our textbooks said it did. It continued, silently, mysteriously, far beyond. And we've only just started listening. Far from being an isolated outlier, Pluto is likely one of many worlds waiting to be explored, and maybe even redefined. It reminds us that classification should follow discovery, not the other way around. Because once you look past Pluto, the landscape only gets stranger.
Arakoth and the Secrets of Planetary Birth. In January 2019, the New Horizons spacecraft flew by an object unlike any other, Arakoth, a peanut-shaped world located 6.6 billion kilometers from Earth. At just 36 kilometers long, Arakoth might seem insignificant, but it turned out to be one of the most pristine and important objects ever visited, a relic from the dawn of the solar system, untouched for over 4 billion years. Arakoth is what scientists call a contact binary, two bodies that gently merged into one. Its two lobes show no signs of violent collision. Instead, they seem to have slowly spiraled into each other and fused. This is crucial. It provides direct evidence that some planetary building blocks formed through gentle accumulation, not catastrophic impacts. Its surface is covered in methanol ice and complex organic molecules, suggesting that chemical evolution was already underway in the early solar system. The reddish hue of Arakoth likely comes from tholins, the same kind of complex organics found on Pluto. These compounds may form the precursors to amino acids and other building blocks of life. Arakoth also tells us about the dynamics of early formation. Its shape and smoothness suggest that the cloud of material it formed from was cold, dense, and slow-moving, an ideal environment for small objects to coalesce gradually. This supports a model called cloud collapse, where regions of the solar nebula locally condensed into clumps that formed planetesimals. Before Arakoth, many scientists believed that objects grew through violent collisions and rapid accretion. But its pristine structure suggests that at least some bodies were assembled with far less chaos. That means the early solar system may have had quieter pockets, places where gravity, not impact, was the dominant architect. Its low density and uniform composition also hint that it never experienced significant internal heating or melting. Unlike larger objects like Pluto or Ceres, Arakoth never had a differentiated core. It remained frozen and unchanged. That makes it a time capsule, preserving conditions from the solar system's earliest moments, like a frozen embryo of planetary formation. What makes Arakoth unique is not just its structure, but its location. It orbits in a relatively quiet part of the Kuiper Belt where it's been undisturbed for billions of years. That's rare. Most small bodies have been jostled, ejected, or broken apart by gravitational encounters. Arakoth avoided all that, making it an ideal laboratory for studying the primordial solar nebula. The New Horizons flyby revealed fine details, no significant craters, very low albedo, reflectivity, and a thin layer of dust. These findings suggest that Arakoth hasn't been impacted much, a surprise given its age. That lack of bombardment further supports the idea that it's been left alone since formation. Arakoth's discovery also pushed the limits of what modern technology can do. It was found using the Hubble Space Telescope specifically to provide a post-Pluto target for New Horizons. Tracking its position and directing a spacecraft toward it across billions of kilometers required precision navigation never attempted before, and it worked. What we learned from Arakoth could change how we search for Earth-like exoplanets. If some planetary systems form from slow, layered accretion rather than collisions, then small, stable planets might be more common than we thought. Arakoth offers a glimpse of a process that could be universal, not just something that happened here. There's still much we don't know.
Is Arrokoth typical of other Kuiper Belt objects, or is it a rare survivor of a calmer-than-usual region? Future missions may one day visit similar bodies and compare them. Until then, Arrokoth remains the clearest snapshot we have of what planetary birth looks like in its earliest, quietest stage. More than just a frozen rock, Arrokoth is a missing page in the solar system's origin story, a page that survived, intact, across eons of cosmic turmoil. In its stillness, it speaks volumes. The possible existence of Planet 9. In 2016, astronomers Konstantin Batygin and Mike Brown proposed a radical idea. There might be an undiscovered planet lurking in the outer solar system, far beyond Neptune. They weren't guessing. The theory came from detailed analysis of the orbits of several trans-Neptunian objects, TNOs. These bodies showed unusual alignments that couldn't be explained by any known gravitational forces. The only plausible answer? Something big is pulling them. According to their models, this mystery planet, dubbed Planet 9, would be 5 to 10 times the mass of Earth, making it a super-Earth. It would orbit the Sun at a distance between 400 and 800 astronomical units, or even farther. One full orbit could take 10,000 to 20,000 years. It's not just far, it's practically invisible, cold, dark, and well beyond the range of our best telescopes. The main evidence for Planet 9 is indirect, based on the orbits of several extreme TNOs. These include Sedna, 2012 VP113, and others whose orbits seem to point in the same direction. Even though these objects are widely spaced, their perihelion points cluster unusually. That kind of alignment isn't expected to persist in a chaotic system unless something massive is acting like a gravitational anchor. When Planet 9 is added to simulations of the solar system, these clustered orbits start to make sense. Not only do the alignments persist, but retrograde and high inclination orbits begin to appear, just like we observe in reality. Without Planet 9 in the model, the simulations fall apart. The odds of these alignments happening by chance are estimated to be less than 0.01%. Some objects also display orbital tilts or eccentricities that shouldn't be stable without an external perturber. In particular, there are bodies that orbit at steep angles or even retrograde, opposite the direction of the planets. These strange orbits don't just look odd, they defy the physics of long-term orbital stability in a solar system with only 8 planets. Planet 9 could also explain the presence of detached objects, whose orbits never come close enough to interact with Neptune. These bodies seem to live in isolation, beyond the gravitational influence of the known planets. But that kind of isolation doesn't occur naturally. It suggests they were pushed outward and then stabilized, exactly what a distant planet would do. Some skeptics argue the clustering of orbits could be observational bias. We're more likely to find certain objects in certain regions of the sky, but ongoing surveys are reducing this bias, and the clustering still holds. New discoveries continue to match the predicted orbital patterns. The more we look, the more consistent the case for Planet 9 becomes. In 2021, a new study suggested that if Planet 9 exists, it could have an elongated orbit with a perihelion around 300 AU. That would mean it might sometimes come closer to the Sun than we thought, improving the chances of spotting it. But even then, it would be very dim, perhaps 1,000,000 times fainter than the faintest stars visible to the naked eye. Some teams are now scanning the sky using infrared telescopes and high-resolution surveys. They're looking for a slow-moving, cold object against the backdrop of fixed stars. It's a difficult task. Planet 9 would move so slowly that it might take years of data to confirm its motion, but it's not impossible. The technology to find it is already here. It just requires patience. If Planet 9 is found, It would be the first new planet discovery in the solar system in over 170 years. It would also change our understanding of solar system formation, suggesting that giant planets can form or be captured much farther out than previously thought. It would also mean our model of 8 planets is incomplete. Some theories even suggest that Planet 9 didn't form here at all. It may have been captured from another star early in the Sun's history. That would make it a kind of interstellar refugee, a visitor that settled into our system and began reshaping its outer edge. If true, Planet 9 could be the most alien planet in the solar system. We don't know yet if Planet 9 exists, but the gravitational clues keep adding up. And if it doesn't exist, then we're faced with an even bigger problem. What is doing all of this? The mystery is real, the data is solid, and something, whether a planet, a disk, or something stranger, is shaping the edge of our solar system.
What's pulling on these distant objects? Across the outer reaches of the solar system, dozens of distant objects appear to be pulled by something we can't see. These objects, many of them in the category of extreme trans-Neptunian objects, or ETNOs, exhibit orbital clustering, strange tilts, and high eccentricities. The gravity of the known planets can't account for their behavior, so the question remains, what's pulling on them? One obvious suspect is Planet 9, a theoretical massive body exerting gravitational influence from far beyond Neptune. But even without assuming a new planet, the observed data demands some kind of perturbing force. That could include a group of smaller objects, a distributed mass like a debris disk, or even an interaction with the galactic gravitational field. Some ETNOs have inclinations above 30 degrees, with orbits tilted well outside the solar system's standard plane. Others move in nearly retrograde directions, opposite the rest of the planets. These characteristics are hard to explain unless something disturbed them, either gradually over millions of years or suddenly during a chaotic event. A few of these distant objects also share a curious trait. Their orbital nodes, or the points where their paths cross the plane of the solar system, are strangely aligned. This suggests a common influencer rather than random chance. Models have shown that such alignments are statistically unlikely without external gravitational shaping. Some scientists have proposed that instead of a single planet, the outer solar system might contain a cluster of small planetary mass objects. Each one may be too small to detect directly, but their combined gravitational influence could explain the observed anomalies. This is known as the distributed mass hypothesis. Others argue that the cause may be even farther out. The gravity of the Milky Way itself exerts weak but steady tidal forces on the solar system. Over millions of years, this could slowly alter the orbits of loosely bound objects, especially those in the inner Oort cloud. In this case, we're not being pulled by a planet, but by the entire galaxy. The problem with many of these theories is that they lack predictive power. Planet 9, for example, makes clear orbital predictions that can be tested. A diffuse mass, or galactic tide, on the other hand, is harder to confirm or rule out. Still, each new discovery, especially those with extreme orbits, adds pressure on existing models to explain what's going on. Then there are the wild cards. Some researchers have considered the possibility of primordial black holes, tiny black holes left over from the early universe. If one were orbiting the Sun at a few hundred AU, it would behave like a massive object, gravitationally speaking, but remain completely dark and undetectable with traditional methods. Other models explore the idea that the Sun once had a stellar companion, a second star that influenced early solar dynamics before drifting away. That companion could have left a long-lasting imprint on the outer orbits.
It's speculative, but if true, some of the strange orbital behavior we see today might be leftovers from a binary star past. Even more conservative models struggle to account for everything. The observed orbital distributions don't match what would happen in a purely random, unperturbed system. And while statistical flukes can happen, dozens of flukes moving in similar patterns raise suspicion. If it's not a planet and not randomness, then something else is at play. Astronomers are now turning to deep sky surveys and AI-based algorithms to identify subtle patterns across large datasets. As more distant objects are discovered, the models will be refined. Either the clustering will dissolve or it will strengthen. For now, the tension between theory and observation is one of the most exciting in planetary science. Whatever is pulling on these distant objects, it has already rewritten the questions we ask about the solar system. It's forcing scientists to rethink its boundaries, its architecture, and its history. And whether the answer turns out to be a hidden planet, a cloud of debris, or something we haven't imagined yet, the edge of the solar system is trying to tell us something. Theories about a giant hidden planet in the dark. The idea that a giant hidden planet might be lurking in the far reaches of the solar system is no longer fringe science. It's a serious hypothesis with growing observational support. Some models suggest this planet could be as massive as Neptune, yet remain undetected because of its incredible distance. But if it's there, why haven't we seen it? The short answer? It's in the dark. This hypothetical world, sometimes referred to as Planet X or Planet 9, would be orbiting in an area with extremely low solar illumination. At hundreds of astronomical units from the Sun, sunlight is too weak to reflect much light from its surface. If it's composed mostly of rock and gas rather than bright ice, it may be nearly invisible in optical wavelengths. One leading theory proposes that this planet formed closer to the Sun, alongside the gas giants, and was later ejected outward by gravitational interactions. In this scenario, it didn't escape the Sun's gravity entirely, but settled into a distant, stable, and highly elongated orbit. That could explain why its path avoids detection and why it still shapes the orbits of distant objects. Another possibility is that the planet didn't originate in the solar system at all. It may have been captured from another star system during the Sun's early years in a dense stellar nursery. Computer simulations show this type of capture is rare but possible. If true, the hidden planet could be an interstellar migrant, a cosmic drifter caught by the Sun's gravity long ago. More exotic theories include the idea of a super-Earth that failed to accrete into a gas giant. Its formation was interrupted, and it remained smaller than Neptune but larger than Earth, a class of planet that's common in other star systems but missing from our own. Planet 9 might represent that missing link, a super-Earth that got pushed into exile. The orbital characteristics of known distant objects seem to point toward a single large perturber, rather than many small ones. This supports the idea of a dominant gravitational source, and multiple studies have concluded that a body 5 to 10 Earth masses could produce the observed effects. The consistency across independent analyses has kept this theory alive. So, why haven't we spotted it? The answer lies in its apparent magnitude. It could be 1,000,000 times fainter than the dimmest stars visible to the naked eye. It would appear as a slow-moving, cold dot, possibly hidden among millions of stars in the background. And if its orbit takes it far from the ecliptic, most surveys would have missed it entirely. Infrared telescopes may be the key. A massive planet emits heat in the form of infrared radiation, even if it's not reflecting much sunlight. Surveys like WISE, Wide Field Infrared Survey Explorer, have been combed for clues, and while they've ruled out some candidates, the search area remains vast. Newer missions may finally detect its thermal signature. The Vera C. Rubin Observatory, expected to go fully operational soon, is designed to scan the sky with unprecedented detail. Its wide-field imaging capabilities will be ideal for detecting slow, distant objects over time. Some astronomers believe that if Planet 9 exists, Rubin will find it, or at least rule it out with high confidence within the next few years. Other possibilities haven't been ruled out, including multiple smaller planets, a dense cloud of debris, or even a primordial black hole the size of a grapefruit, but with the mass of several Earths. These are more speculative, but they reflect how much we still don't know about the outer solar system. The gravitational effects are real. The source remains elusive. The hidden planet theory isn't just about adding a ninth planet. It's about explaining the unexplained, filling in the gaps left by current models. If a giant planet is shaping the edge of the solar system, it would challenge everything from planetary formation to orbital dynamics. And it would mean the map of our cosmic backyard is still unfinished. Until then, the theories continue, driven by data, refined by models, and tested against the sky. The orbital anomalies we can't explain. Not all orbits in the solar system follow neat, predictable patterns. In fact, many of the objects beyond Neptune show orbital behaviors that defy explanation under current gravitational models. These include unexpected tilts, extreme elongations, and clustering that shouldn't occur without a guiding force. And yet they're real, observed, measured, verified. One of the most puzzling features is orbital clustering, where distant objects closest approach to the Sun, their perihelion, aligns in space. Statistically, this shouldn't happen unless something is keeping them grouped. The idea that these orbits are randomly distributed is now mathematically unlikely. Yet there's no clear explanation for what's organizing them. Another anomaly is the presence of high-inclination objects, those that orbit at sharp angles to the solar system's plane. While small tilts are common, some objects have inclinations over 40 degrees, or even orbit retrograde in the opposite direction. These extreme paths are difficult to sustain unless an external force or event has altered them. Some objects also have very distant perihelia, meaning they never come close enough to be influenced by Neptune. These so-called detached objects seem immune to the gravitational shaping of the known planets. Their isolation is a mystery. What placed them on such wide, stable orbits, and what's keeping them there? Even more curious are the objects that appear to resonate with one another. They complete orbits in specific ratios, despite being hundreds of AU apart. That suggests gravitational synchronization, but synchronized with what? The known planets don't account for it. The resonance patterns seem to point toward an invisible conductor. Computer models that simulate the solar system without Planet 9 fail to reproduce these anomalies. When Planet 9 is added with certain parameters, the models align closely with real data. The clustering, tilts, and orbital spacing all start to make sense. But without direct detection, it remains a hypothesis, and the anomalies remain unanswered questions. There are also sudden breaks in orbital populations. Certain types of orbits simply stop appearing beyond specific distances or inclinations. It's as if something cleared out a zone or stabilized it, preventing new bodies from entering. This kind of sculpting suggests a massive long-term influence, not just random chance. The possibility of a missing disk of mass has been considered. Some astronomers propose that a vast ring or torus of small icy bodies might be distorting orbits subtly over time. This would explain the anomalies without requiring a single large planet. But such a structure would also need to be remarkably uniform to produce the observed effects, and that's hard to justify. Galactic forces have also been invoked. As the solar system moves through the Milky Way, it experiences tidal forces from the galactic disk and nearby stars. These forces are weak but constant. Over billions of years, they might stretch or tilt orbits in the outer reaches, but they can't explain clustering or resonance, only slow, general effects. Some astronomers have also floated the idea of ancient events, such as past encounters with rogue stars, or even with an early companion star to the Sun. These one-time events could have flung or stabilized distant bodies into peculiar orbits. But if that's the case, the effects should be randomized by now, not still clearly patterned. The challenge is that each explanation only solves part of the puzzle. No single theory accounts for all the anomalies, the tilts, the clustering, the perihelia, the resonances, the cutoffs, and yet they persist across years, across telescopes, across independent surveys. The patterns are too consistent to ignore. Whatever is behind these orbital mysteries, it's clear our current understanding is incomplete. These aren't glitches or measurement errors, they're features of the outer solar system. And until we find the source, these distant orbits will continue to behave like fingerprints left by a missing gravitational hand. How do we discover objects this far without seeing them? Many of the objects that shape the outer solar system are too faint to be directly seen with current telescopes. They're small, dark, and incredibly far away, some taking thousands of years to orbit the Sun. So how do astronomers know they're even there? The answer lies in indirect detection, a method that looks for gravitational fingerprints rather than visible light. The most powerful tool is orbital mechanics. When a known object behaves strangely, when its orbit is tilted, stretched, or clustered with others, that's a clue. It means something is affecting its motion. Even if the source remains invisible, its influence can be measured. This is how Neptune was discovered in the 1800s, by noticing Uranus wasn't moving the way it should. Today, astronomers use wide-field sky surveys to detect faint moving dots over time. These surveys take thousands of high-resolution images across months or years. Software then compares those images to spot anything that shifts position. Objects that move slowly and don't match known satellites or asteroids are flagged for further analysis. But at the extreme edge of the solar system, motion is painfully slow. An object like Sedna barely moves at all in a year. So astronomers look for patterns of motion, slight deviations, consistent accelerations, or orbital resonances. These subtle clues help reconstruct orbits, even when data is sparse or noisy. It's like assembling a puzzle from a few scattered pieces. Once an object is confirmed, its orbit is tracked and compared to others. Are their perihelia clustered? Are their inclinations aligned? If so, that's evidence of common gravitational influence. This method doesn't reveal the mass doing the influencing, but it helps define where to look and what kind of object could be responsible. Infrared surveys are another strategy. Even in deep space, large objects emit heat. Telescopes like WISE and Spitzer scan the sky in infrared, picking up the faint glow of objects that reflect little or no sunlight. These methods helped find brown dwarfs and distant asteroids, and may one day spot a hidden planet or massive body far from the Sun. Astronomers also rely on gravitational modeling. They build computer simulations of the solar system that test different scenarios. What if a planet of X mass existed at Y distance? How would that affect known orbits? They run thousands of variations, and if one produces orbital patterns that match reality, it suggests something similar might exist out there. Occasionally, the search goes beyond light and gravity. Some researchers use occultation techniques, watching for brief dips in light when a distant object passes in front of a star. These events last just seconds, but can reveal the presence of small, otherwise invisible bodies. This method was used to confirm rings around distant dwarf planets like Haumea and Quaoar. The upcoming Vera C. Rubin Observatory will revolutionize this search. It will scan the entire visible sky every few nights, creating an ultra-deep time-lapse of space. This will make it easier to spot slow-moving distant objects, even if they're incredibly faint. It could also catch unexpected motion patterns, suggesting gravitational disturbances. Machine learning is increasingly being used to analyze sky survey data. AI can spot patterns that human researchers might miss, including anomalies in orbital alignments or rare movement behaviors. These tools may help identify hidden populations of objects beyond Neptune, or even point toward completely new types of celestial structures. Despite all this technology, many discoveries still begin with a single point of light moving slowly across the stars. It's a process that requires patience, persistence, and sometimes a bit of luck. But with each new detection, astronomers get closer to mapping the invisible skeleton of the solar system. In a way, we're discovering the far edge of the solar system by its shadows, tracing the effects of bodies we can't see, but which still leave their mark. It's astronomy by inference, and it's revealing a structure far more intricate and far more active than we ever imagined.
The invisible influence on comet behavior. Comets have fascinated humans for millennia. Icy messengers that appear suddenly, blaze across the sky, and then vanish for centuries. But their origin stories are just as dramatic. Many comets come from the deep outer solar system, and their movements may be guided by forces we don't fully understand. Some of these forces are invisible, but their effects are measurable. Comets are generally grouped into two categories: short period and long period. The former come from the Kuiper belt and return every few decades. The latter may not return for millions of years, and many arrive from odd angles, completely off the ecliptic plane. Their unpredictable paths suggest that something is nudging them into the inner solar system. The most likely origin for long-period comets is the Oort cloud, a distant sphere of icy debris surrounding the solar system. But if these objects are so far away, what causes them to fall inward? The most common explanation is external disturbance, perhaps a passing star or the gravitational pull of the Milky Way itself. But these influences are too weak to account for the frequency we observe. Some models suggest that a massive, distant object, like Planet 9, could be gently stirring the Oort cloud. Its gravitational influence might dislodge comets and send them toward the Sun. This would make it a kind of cosmic gardener, shaking the branches of the solar system and sending debris raining inward. In this scenario, comets become signals of deeper structure. Interestingly, some comets come from polar directions, far above or below the solar system's plane. This suggests their orbits were disturbed from unusual angles.
Standard planetary dynamics can't explain that. It hints at external gravitational shaping, or perhaps even unknown massive bodies in non-traditional orbits. The behavior of comets also reveals strange groupings and families. Some comets follow similar paths and appear to come from the same region, as if they were disturbed in batches. One theory is that these batches result from shock waves or gravitational nudges, which push multiple bodies inward simultaneously. But the source of those shocks remains speculative. There are even comets with orbits that suggest interstellar origins. 2I Borisov, for example, didn't follow any solar orbit. It came from another star system entirely. While rare, these discoveries remind us that the solar system is not isolated. It exists in a gravitational sea, constantly interacting with the galaxy around it. Comets also exhibit unexpected changes in brightness and behavior, sometimes outgassing in patterns not predicted by solar heating alone. This raises the possibility of internal or compositional factors, or that their surfaces are shaped by past gravitational interactions we don't yet understand. In some cases, they may have passed close to massive bodies before, ones we never detected. The idea that comets could be used as probes for outer solar system dynamics is gaining traction. By studying their trajectories in detail, astronomers can look backward and model what forces might have sent them toward the Sun. These backward traced orbits often point to regions of gravitational instability or towards suspected locations of unseen mass. The arrival rate of comets is also curious. If the Oort cloud is their only source, the number we see doesn't always match what models predict. This mismatch could mean we're missing something, perhaps a second source, or an unseen structure influencing the flux of comets. Some believe that the comet rate increases after major gravitational shifts. Future missions, like Comet Interceptor, will explore comets fresh from the edge of the solar system. These untouched bodies might carry information about the forces that dislodged them. Studying their composition and structure could help identify common origins or reveal whether they've been perturbed by a single massive source. Comets are more than icy wanderers. They may be tracers of invisible architecture, shaped by forces we haven't yet mapped. And every glowing tail may be a message from a region of the solar system still cloaked in darkness. Long-period comets are among the most mysterious objects in the solar system. They appear suddenly, blazing across the sky, and then vanish, often for tens of thousands or even millions of years. Unlike short-period comets, which return regularly from the Kuiper belt, long-period comets come from deep space, with orbits so large they barely count as bound to the Sun. Their orbits are typically extremely elongated, forming giant ovals that extend thousands of astronomical units from the Sun. Some don't even return. They visit once and escape into interstellar space. Others are loosely bound, returning only after tens of millennia. Their sheer orbital size suggests they originate in a remote spherical region far beyond Pluto, the Oort cloud. The Oort cloud is believed to be a vast halo of icy debris, extending from about 2,000 AU to possibly 100,000 AU. It's never been directly observed, but the existence of long-period comets strongly supports its presence. These comets approach from all directions, forming a near-spherical distribution, exactly what we'd expect from a cloud surrounding the Sun. But how did these icy bodies get there? One leading theory is that they were formed near the giant planets and were ejected into the far reaches of the solar system by gravitational slingshots early in its history. Some remained bound to the Sun by weak gravity, forming the distant shell we now call the Oort cloud. But if this happened, it must have involved massive planetary reshuffling. Another theory is that external forces, like passing stars, helped populate the Oort cloud. During the solar system's early years, it likely formed in a dense stellar nursery. Close encounters with other stars could have scattered icy planetesimals outward. In fact, some Oort cloud comets may be interstellar in origin, captured from other forming systems. Still, many questions remain. For example, why do some long-period comets arrive in waves rather than in a constant trickle? Some researchers suggest that disturbances from galactic tides or nearby stars periodically stir the Oort cloud, sending clusters of comets into the inner solar system. This could even tie into theories about mass extinctions on Earth. There are also open questions about their composition. Long-period comets often have high levels of carbon-rich compounds, complex organics, and pristine ices that haven't been altered by repeated solar heating. This makes them time capsules, preserving the chemistry of the early solar system, or perhaps even of other star systems. Interestingly, long-period comets tend to be more active and unpredictable than their short-period cousins. Some disintegrate completely when approaching the Sun, while others survive multiple passages. Their surfaces often crack, vent, or explode due to intense solar radiation, but the reasons for such variability aren't fully understood. Comets like C 1995-01 Hale-Bopp or C 2020 F3 Neowise gave us rare, bright spectacles, but they also raised new questions. Hale-Bopp, for example, had a huge nucleus and an unusual sodium tail, while Neowise showed persistent outgassing at unexpected distances. These features suggest hidden complexities in their internal structures. Tracking these comets is challenging. Because they appear so rarely, we often only have a few months to study them before they vanish again. Predicting their return is often impossible without precise orbital data. And even then, gravitational tugs from planets and stars may alter their paths. Many of the brightest comets in history are now lost to the void. Future missions like the ESA's Comet Interceptor aim to visit a pristine long-period comet, ideally one just entering the inner solar system for the very first time. This could provide a direct look at an untouched Oort cloud object, and perhaps confirm whether its origin lies with our Sun or a different star entirely. Long-period comets are rare, but each one brings clues from the edge of our cosmic neighborhood or beyond. Every strange curve in their orbit, every unexpected chemical signature could be part of a much larger puzzle we're only beginning to piece together. Why do some comets arrive from above? Most of the solar system's planets and moons orbit in the same general plane, a flat disk-like region known as the ecliptic. Comets, especially those from the Kuiper Belt, often follow this pattern. But long-period comets frequently don't. Some come in at steep angles, others descend almost vertically. A few even arrive from directly above or below the solar system. Why? This behavior is one of the key reasons astronomers believe in the spherical structure of the Oort cloud. If comets were only coming from a flat disk, we'd expect their orbits to stay near the ecliptic. But they don't. They approach from all directions, forming a diffuse sphere of possible entry points. It's as if the solar system is sitting inside a shell of icy projectiles. But how does a cloud of debris become spherical in the first place? The leading theory is that gravitational disturbances, from giant planets, passing stars, or even the Milky Way itself, gradually randomized the orbits of ejected bodies. Over time, the once flattened outer disk of planetesimals became a more isotropic distribution, the Oort cloud. Some of these overhead comets arrive on orbits inclined by 80 degrees, 90 degrees, or more compared to the ecliptic. A few are even retrograde, traveling in the opposite direction of planetary motion. These orbits are dynamically unstable near the inner solar system, yet they still appear. Something is throwing them inward, and it's doing so from unusual angles. One candidate is the galactic tide, the gravitational pull of the Milky Way acting on loosely bound objects at the solar system's edge. Over millions of years, this force can slowly tug on Oort cloud objects, changing their orbital inclinations and drawing them inward, often from unexpected directions. Another factor could be past stellar encounters. If a star passed close to the solar system tens of millions of years ago, its gravity could have jolted a portion of the Oort cloud. This nudge might have caused a shower of comets, many of which would arrive from inclined or polar trajectories. Some scientists believe such events could coincide with periods of increased comet activity. These steeply inclined comets are harder to detect in sky surveys, which often focus on the ecliptic. This means we may be missing an entire population of comets arriving from above or below. Future all-sky surveys may reveal just how frequent and how strange these high-inclination objects truly are. One idea gaining interest is that some polar comets may be influenced by hidden massive objects in inclined orbits themselves, perhaps even a planet on a tilted path, unseen but shaping distant orbits. This could help explain why some comets consistently appear to favor certain high-inclination entry paths. High-inclination comets also carry important chemical clues. Because they tend to be less processed by solar heat, they may preserve more original material than low-inclination comets. Studying their composition can reveal not just their origin point, but also the conditions in the early solar system or even in interstellar space. In rare cases, these comets showed non-gravitational acceleration, subtle changes in speed or direction that can't be explained by gravity alone. These are often attributed to jets of gas, but they raise intriguing questions. Could unseen gravitational forces be acting on them at great distances? Are we observing signs of something we haven't yet mapped? Whether it's galactic tides, past stellar encounters, or hidden planets, something is influencing these comets. Their strange arrival angles are not random noise. They're part of a pattern that reflects the true three-dimensional structure of our solar system and its interactions with the galaxy. When a comet comes from above, it's not just a spectacle. It may be a message from the solar system's outermost layers, a dynamic reminder that even the sky above the sky holds secrets we've yet to decode. The hypothesis of the Sun's companion star. For decades, astronomers have speculated that the Sun may have once had a stellar companion, a second star bound to it in a wide elliptical orbit. This idea isn't far-fetched. Binary star systems are common in the galaxy. In fact, the majority of stars we observe belong to multi-star systems. So why would our Sun be an exception? The idea stems partly from statistics. Solar-type stars often have companions, especially during their early formation. If the Sun formed in a dense stellar nursery, like most stars do, it likely had nearby stellar siblings. One of them could have been close enough to become gravitationally bound for millions or even billions of years. This companion wouldn't have to be bright or massive. It could have been a low-mass red dwarf or even a brown dwarf, too faint to see easily from Earth. If it existed in a highly elliptical orbit, it might spend most of its time far from the inner solar system, only swinging by occasionally and possibly disturbing objects in the Oort cloud. That's where the theory gets interesting. Some researchers proposed that this hypothetical star could explain periodic spikes in comet activity. If it passed near the Oort cloud every tens of millions of years, its gravity could send swarms of comets hurtling toward the inner solar system. Some of those could have collided with Earth, triggering mass extinctions. The presence of such a star could also explain certain gravitational anomalies in long-period comet orbits. Over time, researchers noticed clusterings and patterns that didn't quite fit with known influences. A companion star periodically passing through the system might be enough to account for these statistical oddities. If such a star once existed, where is it now? One theory is that it became unstable and was ejected from the solar system by a close encounter with another star. Over billions of years, even a small nudge could have been enough to break the gravitational bond. If this happened early in the solar system's life, we may now be orbiting alone. Alternatively, it might still be there, just too faint or too far to detect with current telescopes. Some believe that if it exists, it would lie somewhere between 0.5 and 2 light-years away, possibly camouflaged among background stars or hidden behind the galactic center. Others argue we would have seen it by now, and that it's unlikely such a massive object could remain undiscovered. Interestingly, recent data from surveys like Gaia have been used to search for candidate stars that may have passed close to the solar system in the past. While no clear companion has been identified, these flybys are more common than once thought. It's possible the Sun briefly captured a passing star during its early formation, a temporary dance that ended long ago. Some simulations show that even a loosely bound star could remain in a stable orbit for hundreds of millions of years before being ejected. During that time, it could have caused enough gravitational disruption to alter comet paths, stir the Oort cloud, and influence the outer structure of the solar system in ways we're still trying to interpret. If true, this idea changes our view of the Sun, not as a solitary object, but as part of a once shared system. And it also reframes how we understand early solar system evolution, a dynamic, possibly binary origin shaped by long-lost stellar companions. The Sun's calm appearance may hide a much more turbulent history. To date, there is no direct evidence for a current companion star, but the gravitational signatures, comet paths, and extinction cycles remain compelling. Until we either find such an object or conclusively rule it out, the idea of the Sun's hidden sibling remains one of astronomy's most provocative possibilities. And if we do find it, even as a faint brown dwarf, it could rewrite our cosmic family tree and reveal a chapter of solar system history we never knew existed. Nemesis, the twin star that may have existed. In the 1980s, a bold theory captured the imagination of scientists and the public alike, that the Sun once had a dark twin, a hidden companion star called Nemesis. This star, the theory suggested, orbited the Sun on a long, elliptical path, returning every 26 million years. And each time it came near, disaster followed. The idea came from an observed pattern in Earth's history. Some paleontologists noticed that mass extinctions seemed to occur at regular intervals. If true, what could cause such cycles of catastrophe? One proposed culprit was Nemesis, a faint star disturbing the Oort cloud, sending comets toward Earth like a cosmic shotgun blast. Nemesis was theorized to be a red or brown dwarf, far too dim to be easily detected by telescopes of the time. It would orbit the Sun at a distance of 1 to 2 light-years, taking tens of millions of years to complete a single revolution. If such an object existed, it might have passed near the Oort cloud repeatedly, triggering comet storms. This explanation seemed to line up with several mass extinction events, including the one that killed the dinosaurs. The Chicxulub impact 66 million years ago was thought to have come from such a disturbance. If Nemesis existed, it could be responsible for a recurring cycle of planetary reset buttons. However, the evidence wasn't conclusive. As infrared surveys became more advanced, particularly with the WISE telescope, astronomers began ruling out the existence of a nearby brown dwarf in the areas where Nemesis was predicted to be. No object large enough to account for the effect was found. The idea faded from mainstream astronomy. Still, Nemesis hasn't been entirely abandoned. Some researchers argue that comet impact data is incomplete, and that mass extinctions may not follow perfect cycles. Others suggest that a weaker version of the theory, with a more distant or less massive object, could still hold. The idea evolved from definite twin star to possible long-lost companion. Simulations show that if Nemesis ever existed, it might have been ejected by gravitational interactions with other stars, or destabilized by the Sun's motion through the galaxy. If so, it could now be roaming interstellar space as a rogue object, cold, dark, and no longer part of our system. That would explain why we don't see it today. There are also alternate versions of the Nemesis theory. One posits that the companion may not have been a star at all, but rather a large planet or substellar object, like a super-Earth or brown dwarf in a tilted orbit. If true, it might still be detectable through indirect gravitational effects, or it might have already been ejected long ago. The cultural impact of Nemesis was enormous. It appeared in science fiction novels, documentaries, and even academic papers. While it may not have survived scientific scrutiny, it opened the door to serious questions about the dynamics of the solar system's outer edge and about the Sun's possible past in a binary relationship. What's fascinating is that the core question remains unresolved. Have we always been a one-star system? Binary star systems are common, especially among Sun-like stars. That makes the solar system unusual, unless we've lost our companion or simply haven't found it yet. In the end, Nemesis may be gone, or may never have existed. But the gravitational scars in the Oort cloud, the orbital mysteries of distant comets, and the strange periodicity in Earth's mass extinctions continue to invite speculation. Whether myth or misunderstood evidence, Nemesis left a permanent mark on how we think about hidden companions in space. The edge of the heliosphere, where the Sun stops controlling space. The heliosphere is a giant bubble of charged particles and magnetic fields blown into space by the Sun. It surrounds the entire solar system, shielding it from cosmic radiation and interstellar particles. But like all bubbles, it has a boundary, a limit to the Sun's influence. That boundary is called the heliopause, and it marks where the solar wind gives way to interstellar space. The Sun constantly emits the solar wind, a stream of charged particles that flows outward in all directions. These particles form the heliosphere, pushing against the material that floats in between stars. But the solar wind doesn't travel forever. At some point, it slows down as it collides with particles from the interstellar medium. That's where things get strange. The first spacecraft to reach this boundary were Voyager 1 and Voyager 2. In 2012 and 2018, respectively, they passed through the heliopause and entered interstellar space. The transition wasn't sudden. Instead of a sharp wall, they detected layers of turbulence, rising plasma density, and unexpected shifts in magnetic fields. The boundary was more porous and chaotic than anyone predicted. Voyager 1 found that the heliopause wasn't smooth. It had irregular ripples, like waves on an ocean. It also detected an increase in cosmic rays, high-energy particles from outside the solar system. That confirmed it had crossed into a new environment, where the sun's protective bubble no longer shielded the spacecraft. It was a real-time encounter with another realm. Scientists expected the sun's magnetic field to rotate sharply at the heliopause, but Voyager 1 found that the field direction barely changed. This baffled researchers. It suggested that the boundary was magnetically blended with interstellar space, or that the sun's magnetic influence stretches farther than we thought. Inside the heliosphere, space is dominated by solar wind and magnetic pressure. Outside, the interstellar medium rules, a thin, cold soup of gas, dust, and cosmic rays. The collision between these two environments creates shock waves and charge exchange zones, where particles swap electrons and release energy. It's a dynamic, evolving frontier. Another unexpected finding: the heliosphere is asymmetrical. It's not a perfect sphere, but rather distorted, shaped like a blunt bullet. The sun's motion through the galaxy compresses the front and stretches the tail, much like a boat pushing through water. This structure changes over time, depending on solar activity and local interstellar conditions. The edge of the heliosphere is not fixed. It expands and contracts with the solar cycle, roughly every 11 years. During solar maximum, when the sun is most active, the solar wind is stronger, pushing the boundary outward. During solar minimum, the heliosphere shrinks, exposing more of the solar system to interstellar radiation. This dynamic behavior affects not just spacecraft, but cosmic weather. Changes in heliospheric size influence how much radiation reaches Earth, how comets behave, and even how galactic particles penetrate our system. Understanding this boundary helps us predict space weather and protect satellites, astronauts, and communication systems. In recent years, scientists have tried to visualize the heliosphere in 3D, using IBEX and the upcoming IMAP mission. These missions aim to create a full map of the heliosphere's edge by detecting energetic neutral atoms. The result may be a true weather map of the solar bubble we live in. The heliopause is not just a scientific concept, it's a real frontier, a moving boundary where the sun ends and the galaxy begins. By studying it, we learn not only about the solar system, but about how all stars interact with their surroundings. Every star has a bubble like this, and each one tells a different story. We once thought the solar system ended at Pluto, then at the Kuiper Belt, then the Oort cloud. Now we know it's a plasma frontier, an electromagnetic boundary that changes shape and challenges definitions. The sun may still be glowing here, but its grip on space ends somewhere out there. The shock zone between us and the interstellar medium. Between the flowing solar wind and the quiet drift of interstellar space lies a chaotic transition zone. It's called the termination shock, and it marks the point where the solar wind slows dramatically after colliding with the interstellar medium. What lies beyond it is not calm. It's a region of turbulence, compression, and energetic chaos. The termination shock forms a kind of shock-wave shell around the solar system. Here, solar wind particles that were speeding away from the sun at supersonic speeds are suddenly slowed, heated, and compressed. This creates a turbulent zone filled with magnetic waves, high-energy particles, and strange behavior that defies prediction. Voyager 1 crossed the termination shock in 2004. The spacecraft detected a sudden jump in temperature and particle density, evidence it had entered a new region of space. Voyager 2 followed in 2007 and reported even more chaotic activity. What scientists found was a messy, layered transition, not a clean border. This region, between the termination shock and the heliopause, is known as the heliosheath. It's like a buffer zone between solar influence and interstellar space. But far from being a quiet boundary, it's full of magnetic turbulence and pickup ions, particles that swap electrons and spiral unpredictably through the region. One surprise, the solar wind in this region doesn't simply fade away, it mixes with the incoming interstellar flow in complex ways. The result is a plasma interaction zone where charged particles collide, merge, and sometimes reverse direction. This zone acts as both a shield and a filter for interstellar matter. Energetic neutral atoms, ENAs, formed by charge exchanges in this region, are now being mapped by instruments like IBEX. These maps show a strange ribbon of high-energy particles across the sky called the IBEX ribbon. Its origin is still not fully understood, but it may reveal how interstellar and solar forces align at the boundary. The heliosheath also appears to emit sounds, pressure waves that can be converted into audio frequencies. Voyager data has been used to produce these eerie space tones, capturing the hiss and rumble of particles interacting. It's the sound of the sun fighting the galaxy. Some researchers think this shock zone may act like a cosmic bow wave, similar to what forms in front of a moving ship. As the solar system travels through the galaxy, it generates a front of disturbed space ahead of it. Whether this bow shock is strong or weak depends on the density and speed of the surrounding interstellar medium. Understanding this transition zone isn't just academic, it has implications for deep space exploration, radiation shielding, and the long-term safety of spacecraft. It also tells us how stellar systems interact with the galaxy and how cosmic rays are filtered before reaching Earth. The heliosheath may also hold trapped particles that help explain anomalies in cosmic ray distribution. Some particles appear to bounce back and forth between magnetic fields before escaping. Others seem to spiral along filaments of magnetic flux. The region behaves like a charged particle maze, reshaping what we thought we knew about space physics. Simulations show that the shape and size of the heliosheath are not constant. They change with solar cycles, galactic pressure, and magnetic field strength. That means the shock zone is alive, a dynamic, ever-changing interface between solar plasma and the galaxy's broader flow. The space between stars isn't empty, and the solar system doesn't end with planets or even frozen rocks. It ends in a zone of shock, noise, heat, and magnetic struggle, the last frontier of the sun's reach, and the first glimpse of everything beyond it. Discoveries from Voyager at the edge of the solar system. Launched in 1977, the Voyager 1 and 2 spacecraft were originally designed to explore the outer planets, but they became so much more. After completing their planetary missions, both probes continued outward, eventually becoming the first human-made objects to enter interstellar space. What they found was beyond anyone's expectations. Voyager 1 crossed the heliopause in 2012, followed by Voyager 2 in 2018. This boundary marked the transition from the sun's influence to the interstellar medium, the space between stars. The change wasn't obvious at first. There were no dramatic visuals, but the instruments on board recorded a shift in charged particles and magnetic field strength. Inside the heliosphere, the solar wind dominates. Outside, cosmic rays and interstellar particles flow freely. Voyager 1 detected a 5-fold increase in cosmic radiation, confirming it had left the sun's bubble. At the same time, the direction of the magnetic field barely changed, a mystery still debated today. Why didn't it flip as predicted? Voyager 2's crossing added crucial data. Unlike Voyager 1, it retained a working plasma sensor, allowing scientists to measure the density and temperature of the interstellar medium directly. The readings confirmed a dramatic increase in plasma density, consistent with theoretical predictions. This was a first, direct contact with the galaxy beyond. Both Voyagers also detected plasma oscillations, essentially sounds of interstellar space. These low-frequency waves gave scientists a new way to map interstellar pressure and density. It's not silent out there. It's filled with subtle, continuous vibrations. The probes translated them into audio, allowing us to hear the space between stars. Surprisingly, the data revealed that the interstellar medium isn't uniform. It's lumpy, magnetized, and structured. The Voyagers passed through shocks, turbulence, and boundaries that no one had predicted. Some areas were calm, while others were chaotic, like ocean currents clashing in space. The galaxy, it turns out, is far from smooth. Another major finding was the thickness of the heliosheath, the region between the termination shock and the heliopause. Voyager 1 traveled over 40 AU through this zone, much farther than expected. That suggests the solar boundary is not a thin shell, but a vast, turbulent frontier where solar forces and galactic forces wrestle for control. The Voyagers also showed that the Sun's influence stretches farther than we thought. Even outside the heliopause, they continued to detect traces of solar particles. This blurs the line between inside and outside the solar system. The border isn't a wall, it's a gradient. Perhaps most astonishing is that both spacecraft are still working, more than 47 years after launch. They continue to send data, though power is dwindling. NASA expects communications to cease sometime in the 2030s, marking the end of an era. But until then, they remain our furthest explorers, ambassadors of Earth in deep space. Voyager's golden records, analog messages to any future finders, include sounds of Earth, greetings in dozens of languages, and music. They float silently into the void, carrying the first human message to the stars, on ships made of 1970s hardware still defying time and distance. Their discoveries have redefined our understanding of the solar system's boundary. We now know it's not clean, not simple, and not quiet. It's alive with shocks, waves, and particle flows, a battlefield between solar wind and galactic tide. The Voyagers didn't just reach the edge, they showed us that the edge is more complex than the center. As of now, Voyager 1 is over 24 billion kilometers from Earth. That's farther than any object ever sent by humans. And even though it travels silently through darkness, it continues to whisper back messages that reveal just how little we know about where the Sun's kingdom ends and what lies beyond it. The silence beyond. What lies after the Sun's reach? Once a spacecraft crosses the heliopause, it enters the unknown, the realm of interstellar space. There's no more solar wind, no more planetary influence, just silence. But this silence is deceptive. It's not empty. Beyond the Sun's reach lies a region filled with subtle forces, cold particles, and unmapped mysteries. Out there, the interstellar medium, ISM, takes over, a sparse mix of hydrogen, helium, dust, and cosmic rays. It's thin, 1,000,000 times less dense than Earth's atmosphere, but it's not uniform. The Voyagers have shown that it's clumpy, charged, and unpredictable. There are pressure gradients, density spikes, and magnetized regions we never imagined. Despite this activity, space out there is eerily quiet in terms of electromagnetic signals. No planetary radio bursts, no strong magnetic storms, just faint particle flows and cosmic background noise. The further the Voyagers go, the more we realize that even the galaxy has quiet zones, spaces between stars, between systems, between influences. But this silence is a challenge for detection. It makes finding rogue planets, dark objects, or even interstellar civilizations nearly impossible. If something large and cold is moving through this region, it wouldn't emit light or radiation. It could pass unnoticed unless it interacts gravitationally with something else. Some scientists suspect that interstellar space may host unknown structures, dark clouds, magnetic filaments, or even remnants of ancient star systems. These features are hard to detect from Earth because they don't reflect light, but they might subtly affect the motion of stars or disturb passing comets on their way inward. One tantalizing idea is that interstellar space could be filled with rogue planets, worlds that formed in stellar systems but were ejected and now drift between stars. These could number in the billions across the galaxy. They may carry moons, atmospheres, or even oceans, and yet remain invisible to our current telescopes. There's also the possibility of encountering interstellar dust storms, dense regions of particles that could interfere with spacecraft or obscure distant observations. These clouds might even contain prebiotic material, having drifted for millions of years, shaped by supernova remnants and galactic winds. If life exists elsewhere, its building blocks may travel through this dark ocean. Some researchers propose that parts of interstellar space might carry subtle relics of ancient civilizations, probes, structures, or even radio signals long since dissipated. The odds are low, but the distances are vast. In silence, even a whisper can carry far, if you're listening in the right way. From a physics standpoint, the transition beyond the sun's reach opens up fundamental questions. How does space behave without a dominant magnetic field? Are there hidden interactions between particles we don't yet understand? The farther we go, the more our assumptions about empty space break down. Even gravitationally, things get strange. Beyond the heliosphere, the sun's pull weakens, but not instantly. It fades slowly, allowing loose, long-period objects to remain bound. This includes potential Oort cloud members and even captured interstellar visitors. The zone beyond the sun may not be lawless, just ruled by different laws. And perhaps the greatest mystery of all is what we'll find if we keep going. Will we discover new forms of matter? Will we stumble upon structures built by others? Or will we just drift through an infinite sea of cold silence, pierced only by the echoes of dying stars and the static of cosmic background radiation? The silence beyond the sun is not just quiet, it's waiting. Waiting for new explorers, waiting for better instruments, waiting for the moment when we stop calling it beyond and start calling it home to the next horizon. The interstellar medium and its invasive particles. Beyond the sun's protective bubble lies the interstellar medium, a vast expanse of thin gas, dust, and high-energy particles drifting between stars. It seems empty, but it isn't. This space contains charged atoms, magnetic fields, and even organic molecules, all moving through the galaxy at varying speeds and densities. And some of it gets in. Despite the sun's influence, particles from interstellar space constantly penetrate the heliosphere. These are mostly hydrogen and helium atoms, but some are charged, high-energy cosmic rays. Unlike solar particles, these come from distant supernovae, neutron stars, or even the galactic core. They carry incredible energy, and they're hard to stop. The heliosphere acts like a shield, filtering and slowing many of these invaders, but it's not perfect. When the sun is at solar minimum, its least active phase, the shield weakens, allowing more interstellar particles to get in. This means cosmic ray levels at Earth rise, increasing radiation exposure for astronauts and satellites. These incoming particles aren't just passive visitors. Some interact with solar wind ions, causing charge exchange reactions. A neutral interstellar atom might steal an electron, become charged, and spiral along magnetic field lines, joining the chaotic flow of the heliosheath. These particles are called pickup ions, and they're crucial for understanding boundary dynamics. Spacecraft like IBEX and Voyager have detected these particles and mapped their distribution. IBEX in particular showed that the interstellar medium is not uniform, it's directional and even carries a preferred magnetic alignment. This challenges old models that assumed a quiet, random interstellar background. There's also a puzzle. The heliosphere seems to be surrounded by a warm cloud of gas. Some researchers think the Sun is currently passing through the edge of the local interstellar cloud, a denser-than-normal region of space. This may affect the shape of the heliosphere, the rate of interstellar particle penetration, and even the Sun's long-term interaction with the galaxy. These particles may also leave traces in meteorites and ancient ice cores. By studying isotopes like beryllium-10 or carbon-14, scientists can detect past spikes in cosmic ray flux, evidence of interstellar weather events that may have affected Earth's climate or atmosphere thousands of years ago. In addition, there's growing evidence that interstellar dust grains penetrate the inner solar system. These tiny fragments, sometimes no larger than a molecule, can travel at tens of kilometers per second. NASA's Ulysses and Cassini missions detected streams of such particles, raising questions about their origin and long-term impact. Some of this dust carries complex organic molecules, such as polycyclic aromatic hydrocarbons. These are building blocks of life, forged in ancient stars and blown into space by supernovae. The fact that they can enter the solar system means that interstellar material may seed planetary systems, including ours, with the ingredients of biology. Astronomers also wonder how these particles might affect future interstellar probes. High-speed dust grains could pose a hazard to spacecraft traveling at tens of thousands of kilometers per hour. Shielding and predictive modeling will be key for missions aiming to reach Alpha Centauri or beyond. What's remarkable is that these tiny, often invisible particles are slowly sculpting the boundary of our solar system. They push against the solar wind, alter magnetic flows, and sometimes make it all the way to Earth. They remind us that space isn't empty. It's a battlefield of particles, energy, and invisible pressure. And with every interstellar atom that enters our domain, we're reminded the solar system doesn't float alone. It drifts through a galaxy full of ancient matter, cosmic radiation, and the chemical traces of dead stars. How the solar wind changes as it fades into the dark. The solar wind is one of the Sun's most persistent creations, a stream of charged particles launched into space at up to 800 kilometers per second. Near Earth, it's a constant force, shaping auroras and space weather. But as it travels farther out, it weakens, spreads, and eventually breaks down into something else entirely. Near the Sun, the wind is fast, dense, and structured. It carries magnetic fields that form spirals, known as Parker spirals because of the Sun's rotation. But by the time it reaches the outer solar system, those spirals are stretched and warped. The wind becomes turbulent, mixing with older waves and interacting with planetary magnetospheres. Past Neptune, the solar wind starts to slow and lose its coherence. This is where it enters the heliosheath, the region beyond the termination shock. Here, the wind is no longer supersonic. It's been slowed by collisions with the interstellar medium. The pressure rises, temperatures change, and the flow becomes more chaotic and compressed. At the termination shock, solar wind particles are heated and accelerated, creating a foamy, energized plasma environment. Voyager 1 detected dramatic changes here, sudden increases in particle density and magnetic field strength. It marked a shift from the familiar solar-controlled zone to the no-man's land of transition. Inside the heliosheath, the solar wind starts to interact directly with interstellar particles. Some particles from the ISM enter and collide with solar ions, creating pickup ions and energetic neutral atoms, ENAs. This creates a swirling soup of particles that doesn't behave like anything we see closer to Earth. These interactions also lead to wave-like structures as magnetic fields twist and reconnect. The Voyager spacecraft recorded strange bursts of plasma oscillations, not regular wind, but something more like magnetic turbulence. The further you go, the less the solar wind behaves like a wind at all. Eventually, the solar wind reaches the heliopause, the edge of the Sun's influence. Here, it effectively stalls out, no longer pushing against interstellar particles. Outside that boundary, solar origin plasma becomes rare. The galaxy takes over. The wind is absorbed, deflected, or blended into the cosmic sea beyond. But not all solar particles disappear. Some continue to drift far beyond the heliopause, joining the interstellar medium as rogue ions. In a way, the solar wind doesn't stop. It diffuses, leaving chemical and energetic traces of the Sun billions of kilometers from home. Interestingly, the solar wind also carries variations from solar cycles across the solar system. A solar storm near Earth might be felt in the outer heliosphere months or years later, depending on speed and density. This makes the solar wind a messenger of solar history, stretched out over time and space. Instruments like IMAP and Voyager help trace how this wind changes, measuring speed, density, and particle type across vast distances. These readings inform everything from climate models to spacecraft shielding. They also help scientists understand how other stars influence their own planetary systems. Ultimately, the solar wind tells us something profound. The Sun is not just light and gravity, it is influence. Its breath reaches across billions of kilometers, touches everything it birthed, and fades slowly into the dark, leaving behind a trail of charged whispers in the silence of space.
Could interstellar planets be watching us? It sounds like science fiction, but the idea of interstellar planets observing us has serious roots in astrophysical theory. These would be planets not bound to any star, drifting alone through the galaxy. Called rogue planets, they may number in the billions, and some could be passing silently near the solar system right now. Rogue planets form in two ways, either as normal planets ejected from their home systems by gravitational chaos, or as failed stars that never ignited. Some are massive gas giants, while others could be rocky Earth-like worlds. Without a parent star, they wander the galaxy, cold, dark, and nearly invisible. The big question is, could one of them harbor life? It seems unlikely. No star means no light, no warmth. But some scientists argue that a rogue planet with a thick atmosphere or internal heat could support microbial ecosystems beneath ice layers or in underground oceans. These would be self-contained biospheres, isolated in the dark. If so, they wouldn't just exist, they could evolve independently, develop complex chemistry, or even produce intelligent life. And here's where it gets even stranger. If such beings existed, how would they detect other systems? Stars like our Sun would be visible beacons to them, easy to spot with basic instruments. From their perspective, we are the ones under a spotlight. Earth's radio leakage, infrared emissions, and even atmospheric composition might be detectable to observers in deep space,
especially if they're actively scanning. This raises the question, are we being watched by life forms we don't even know exist? Some researchers propose that advanced civilizations on rogue planets or probes launched by them might pass through systems like ours to study planets up close. The idea isn't that they're hostile or invasive, just curious. They may be gathering data as they drift, or even slingshotting through systems using gravity assists. The challenge is that rogue planets are nearly undetectable unless they pass in front of stars, causing brief dips in brightness known as microlensing events. Several candidates have been found this way, but if one were nearby and actively scanning us, we might not even know it, unless it wanted to be seen. There's also the possibility that some rogue planets are equipped with artificial satellites or probes, orbiting observation platforms deployed to gather data. These satellites would be far easier to maintain than long-distance interstellar probes, and if one passed near Earth, it could study us in great detail without ever being noticed. Could one of these rogue worlds be passing through our cosmic neighborhood right now? It's possible. Estimates suggest there may be up to 100,000 rogue planets for every star in the galaxy. Most are small, cold, and unremarkable, but some might be carrying something more: biology, technology, or even awareness. We have no evidence that this has happened, but in science, absence of evidence is not evidence of absence. The distances are enormous, the objects hard to detect, and the time frames vast. Even if such a planet only approached once every million years, we might never know, unless it left something behind. Some speculate that strange objects like Oumuamua, an interstellar visitor with unusual acceleration, could be related to such rogue travelers. Others suggest that if rogue planets are intelligent, they may avoid contact intentionally, observing without interfering, a kind of galactic non-interference protocol. The question isn't just, are we alone? It's, are we visible? And if the answer is yes, then we have to consider who or what might be watching from the dark between stars, writing cold planets that were never meant to be found. How can we detect cold, dark objects in deep space? The universe is filled with objects we can't see, not because they're far away, but because they're cold, dark, and silent. Rogue planets, brown dwarfs, black dwarfs, and ancient comets may be drifting through the void, emitting little to no light. So how do we find them? The answer lies in non-visual astronomy. Visible light is just one small slice of the electromagnetic spectrum. Cold objects don't shine in the visible, but they may still emit infrared radiation or affect their surroundings through gravitational influence. By switching to infrared, radio, or gravitational detection methods, we begin to reveal what was once hidden. Infrared telescopes like WISE, or Wide Field Infrared Survey Explorer, have already found hundreds of previously unseen brown dwarfs, failed stars too small to ignite nuclear fusion. Some of these lie just a few light years from Earth, yet were invisible to traditional telescopes until recently. Imagine what else could be nearby. Cold planets may also be detected via gravitational microlensing. When a massive object passes in front of a distant star, its gravity bends the starlight, briefly making it brighter. This tells us something passed by, even if we never see the object itself. It's like watching a shadow without seeing what cast it. Another strategy is looking for motion. Even dark objects may block starlight momentarily if they pass between us and a background star. This is called stellar occultation. These events are rare and brief, but with wide-field surveys scanning the sky regularly, we can spot more of them and catch invisible wanderers in the act. Gravitational anomalies also offer clues. If known objects, like trans-Neptunian bodies, move in unexpected ways, it may point to the presence of unseen mass. This is how Neptune was discovered in the 1800s, and how some researchers today are looking for the hypothetical Planet 9. We can also detect cold objects indirectly through their impact on dust and gas. A massive body moving through space may compress or scatter interstellar material, leaving a trail that instruments can detect. Radio telescopes and dust mapping missions are now starting to uncover these hidden interactions. Soon, new instruments will change the game. The James Webb Space Telescope, for instance, is optimized for infrared, perfect for spotting cool, dim objects. It could detect small rogue planets, dark comets, or even large moons that were previously beyond our technological reach. Future missions, like Nancy Grace Roman Space Telescope and Euclid, will further expand our sensitivity to dark objects. These observatories will scan wide swaths of sky, looking for lensing events, movement patterns, and deep infrared signatures, mapping the unseen population of our cosmic neighborhood. Another emerging field is gravitational wave astronomy. If a cold, compact object, like a black dwarf, collides or interacts with another body, it might produce ripples in spacetime. While most current detectors are tuned for massive events, like black hole mergers, more sensitive instruments could someday pick up subtler signatures. The universe is full of what we can't see, and always has been. From rogue planets to orphaned moons to ancient brown dwarfs, a hidden architecture surrounds us. It shapes the galaxy, steers comets, and maybe even hides clues to life itself. To detect the invisible, we have to look sideways, for heat instead of light, motion instead of shape, gravity instead of glow. And with every new detection, we pull another object from the dark and into the story of our expanding universe. The technology we still lack to see the invisible. For all our progress, much of the universe remains hidden, not because it's too far, but because it's too faint, too cold, or too strange for our current instruments. There are objects moving silently through the galaxy that emit no light, reflect almost nothing, and interact only weakly with their surroundings. We suspect they're there, but we can't yet prove it. Our greatest limitation is sensitivity. Even the best telescopes miss low-energy objects, especially those beyond the infrared range. We need instruments that can detect ultra-cold black body radiation, which means developing detectors thousands of times more sensitive than what we currently use in space. The James Webb Space Telescope is a major leap forward, but it's still just the beginning. It can detect exoplanets, brown dwarfs, and early galaxies, yet objects like primordial black holes, black dwarfs, or small rogue planets remain out of reach. They either emit too little energy or blend into cosmic background noise. To see the truly invisible, we need a revolution in infrared and submillimeter astronomy. This includes cryogenically cooled detectors, possibly stationed far from Earth, free from our planet's heat and radiation. These instruments must be able to detect a single photon of warmth from a body that hasn't seen starlight in 1 billion years. We also lack wide-field all-sky surveillance at high sensitivity. Most sky surveys focus on limited patches of the sky or only track known objects. A future mission might scan every direction, every night, looking not for bright flashes, but for tiny shadows, slow drifts, or gravitational effects from unseen masses. Another missing piece is interstellar radar. While radar is incredibly effective in the inner solar system, its range drops off quickly. A powerful space-based radar system could, in theory, illuminate nearby dark objects, but the power requirements and precision targeting needed are far beyond our current capabilities. We also lack the ability to image gravitational fields directly. Right now, we detect gravity only by its influence, how it bends light or alters orbits. If we could map gravitational anomalies in 3 dimensions, we might finally see the structure of dark matter, rogue worlds, or even the gravitational wake of ancient collisions. Our best hope may lie in constellation telescopes, networks of coordinated spacecraft spread across the solar system, sharing data in real time. They could triangulate faint signals, detect passing shadows, and create multi-perspective maps of transient or hidden objects. We're not there yet, but it's coming. Another area lacking is particle detection in deep space. Earth-based detectors, like those searching for neutrinos or cosmic rays, are limited by atmospheric interference. A future deep space neutrino observatory could detect interactions from otherwise invisible sources, including cold fusion remnants or exotic physics. We also haven't fully explored quantum sensing in space. Quantum gravimeters and entanglement-based sensors might offer unprecedented precision in detecting tiny changes in mass or energy, ideal for finding faint or strange objects that don't behave like anything we know. What we lack most isn't just instruments, it's reach. To study these objects up close, we'll need fast, durable probes that can travel tens or hundreds of astronomical units quickly. We don't yet have propulsion systems that make that practical, but projects like Breakthrough Starshot and nuclear electric engines may change that. In the end, much of the universe remains invisible, not because it hides, but because we're still building the eyes to see it. With every new leap in technology, the veil thins, and what we find behind it may change our understanding of space, time, and existence itself.
Why the solar system may have been invaded by outsiders. The solar system feels like a closed system, planets orbiting the sun, shaped by its gravity alone. But the truth is, our cosmic neighborhood is porous, constantly intersected by material from the galaxy. Over billions of years, it's entirely possible that foreign objects have entered, stayed, or even reshaped what we thought was ours. The clearest evidence comes from interstellar visitors like Oumuamua and Borisov. These objects didn't originate here. Their trajectories show they came from other star systems. And yet they passed through our solar system silently, undetected until they were already flying away. How many others have we missed? Some of these outsiders might have crashed into planets or moons, delivering exotic materials. Others may still be here, hiding in wide, looping orbits mistaken for native objects. Astronomers have long debated whether certain comets or asteroids might be captured interstellar relics, trapped by the sun's gravity eons ago. The Oort cloud itself might be partially alien. Its outer regions extend so far that the sun's grip is weak, meaning even a modest gravitational nudge from a passing star could insert a foreign object. Simulations suggest that stars pass close enough to our system every few million years. When they do, things get messy. There's also the possibility that rogue planets have slipped into our system in the deep past. Some could have passed through, disturbing orbits and leaving again. Others might have stayed, especially if they settled into stable, distant orbits beyond Neptune or the Kuiper Belt. We may have unknown visitors still circling us now. Some astronomers suggest that objects like Sedna or 212 VP113 may have been influenced or even placed by external forces. Their orbits don't make sense under current models of solar system formation. They may carry orbital scars from encounters we don't remember. Could life have arrived the same way?
The theory of panspermia suggests that life, or its building blocks, could hitch a ride on asteroids or comets between star systems. If so, Earth may not be the origin of life here, but merely one stop on a galactic biological highway. More provocatively, could intelligent life have visited us before? Some researchers entertain the idea that alien probes could enter systems like ours for study. We might not recognize them, especially if they're designed to be small, stealthy, or camouflaged as natural objects. The absence of clear signs doesn't rule out their past presence. Evidence is sparse, but the probability is high. Over 4.5 billion years, with tens of thousands of stellar flybys, even rare events become statistically likely. The question becomes less about if and more about how many and what did they leave behind. Some anomalies may be waiting to be reinterpreted. Irregular moons, distant clusters of small bodies, or unexplained orbits might hint at past intrusions. The Kuiper Belt and Oort cloud are vast and largely unmapped. Any number of foreign objects could be hiding there, undistinguishable from the rest. We imagine the solar system as a closed set, but in reality, it's more like a corridor, open, intersecting, and part of a wider galactic traffic network. It's not unthinkable that we've had guests. Some may have left no trace. Others may still be circling, watching, or simply waiting in the dark. In the future, as we map the deep solar system in more detail, we may finally uncover evidence of these ancient encounters and rewrite the boundary between native and alien forever. Interstellar objects like Oumuamua and Borisov. Until recently, we thought every object in the solar system was native. Then came Oumuamua in 2017, the first confirmed interstellar object ever observed passing through our planetary neighborhood. It wasn't just unexpected, it was a cosmic wake-up call. Other star systems are sending objects our way, and we've only just started noticing. Oumuamua was discovered by the Pan-STARRS telescope in Hawaii. It had an unusual trajectory, coming from outside the solar system on a hyperbolic orbit, meaning it wasn't gravitationally bound to the Sun. It came in fast, curved around the Sun, and left just as quickly, never to return. It was the first confirmed visitor from beyond. Then, in 2019, came a second, 2I Borisov, a comet with a visible tail and familiar behavior, but with an origin far beyond our system. Unlike Oumuamua, Borisov looked like a typical comet. It provided the first opportunity to study interstellar material in real time, and showed that other systems form icy bodies much like our own. These discoveries changed astronomy. For decades, we suspected interstellar objects existed but had never detected one. The fact that we spotted two in just a few years suggests they may be more common than we thought, and that space between stars may be filled with wandering fragments from ancient systems. Both objects behaved very differently. Borisov's composition matched known solar system comets, though it was more carbon-rich. Oumuamua, however, lacked a visible tail or coma, didn't emit gas, and displayed non-gravitational acceleration. It changed speed in ways comets typically don't, without any obvious outgassing. These anomalies sparked intense debate. Some researchers suggested that Oumuamua was a fragment of a nitrogen iceberg, or a hydrogen-based body that sublimated too subtly to detect. Others proposed more exotic explanations, including the idea that it could be artificial, or a technological object from another civilization. What's clear is that interstellar objects carry pristine clues from other star systems. They're not altered by the Sun or shaped by planets here. Studying them allows us to directly examine alien chemistry, formation processes, and structural behavior. They are messengers from worlds we cannot yet reach. Astronomers are now designing dedicated missions to intercept future visitors. Projects like ESA's Comet Interceptor are designed to wait in space and rush toward the next interstellar object that comes close. The goal: get up-close images, sample material, and analyze alien debris in real time. Future telescopes like the Vera C. Rubin Observatory will increase our chances of detecting these objects earlier, allowing us more time to study their paths and possibly divert missions toward them. Early detection is key. By the time we spotted Oumuamua, it was already leaving. These interstellar visitors may also play a role in planetary seeding. If they carry organic molecules, water, or even microbial life, they could be agents of panspermia, spreading biology from star to star. That makes them not just geological curiosities, but biological time capsules. There's also a growing belief that some interstellar objects may have been captured by the Sun's gravity and now reside in long, dark orbits. We may be surrounded by silent visitors that we haven't recognized yet, camouflaged among comets and asteroids, waiting to be identified. We used to think our solar system was an isolated island, but Oumuamua and Borisov showed us otherwise. We live in a galactic highway, where fragments of other worlds occasionally pass through, some by chance, others perhaps for a purpose we don't yet understand. The theory that Oumuamua was an artificial probe. When Oumuamua was first observed, its strange properties puzzled scientists. It had no tail, no outgassing, and a peculiar shape, possibly cigar-like or pancake flat. Most oddly, it accelerated slightly as it left the solar system with no visible explanation. This led some to ask, was it artificial? The theory was brought to the spotlight by Avi Loeb, a Harvard astrophysicist who suggested that Oumuamua could be a piece of alien technology, perhaps a light sail or defunct probe sent long ago by an advanced civilization. His argument wasn't about proof, but about anomalies that standard models failed to explain. Traditional explanations struggled to fit. Some proposed that it was a hydrogen iceberg evaporating invisibly. Others thought it might be a fragment of an exopluto shedding nitrogen gas, but none fully accounted for the trajectory, lack of coma, and unusual reflectivity. The object seemed to defy classification. Loeb argued that the simplest explanation for a non-gravitational push without visible thrust was radiation pressure, the gentle push from sunlight, acting on a thin, flat object, much like a solar sail. This implied the object had to be extremely lightweight, possibly artificial in origin. His paper sparked both excitement and controversy. Critics claimed the data could be explained naturally, with unusual material properties or comet behavior we haven't observed before. Others praised the idea for challenging assumptions and broadening the scope of investigation beyond conventional limits. What made Oumuamua unique wasn't just its motion, but its lack of emissions. Every known comet that accelerates does so because of gas jets from melting ice. But Oumuamua's acceleration had no visible outgassing and no detectable dust. That made the artificial theory hard to dismiss entirely. Loeb wasn't saying it was an alien spacecraft, just that, based on the evidence, we should not rule it out prematurely. He argued for a more open scientific framework, one where extraordinary claims are not ignored, especially when the data itself is extraordinary. His proposal raised broader questions. If Oumuamua were artificial, it might be a relic, drifting for millions of years. It may no longer be functional, or may never have been meant for communication. It could be part of a network of probes, launched to gather information silently as they pass through habitable systems. This idea aligns with the Bracewell probe hypothesis, which suggests that civilizations may send autonomous observers instead of signals. If so, we may be visited more often than we realize, but by objects that deliberately avoid interference, observing silently, efficiently, and anonymously. The truth is, we may never know. Oumuamua was already leaving when we discovered it. No spacecraft could catch it. We have only a few weeks of data and no physical samples. It left more questions than answers, but the questions it raised may guide future exploration. What if we launched an interceptor next time, or stationed telescopes ready for such visitors? Every anomaly should be an opportunity to expand our scientific vocabulary, not shrink it. Whether natural or artificial, Oumuamua taught us to expect the unexpected. And maybe, just maybe, it reminded us that we're not the only ones watching the sky.
Are we really ready to find something out there? Everyone wants to find something extraordinary in space. An alien signal, a rogue planet with life, a mysterious structure. But here's the deeper question. Are we truly ready to deal with it? Discovering intelligent life or unexplained phenomena at the edge of the solar system could change everything, and not just in science. First, there's the psychological shock. For over a century, we've imagined aliens through science fiction as threats, saviors, or enigmas. But what if we encountered something that didn't fit any of those scripts? Something truly alien, not just in biology, but in thought, physics, or behavior. The discovery wouldn't just affect scientists. Religions, governments, cultures, and ideologies around the world would be forced to reevaluate their place in the universe. For some, it might be exhilarating. For others, terrifying. And the truth is, we don't know how humanity would respond to something we didn't understand. Even at a technical level, we're not fully prepared. If we received a strange signal or encountered an artificial object, do we have protocols? The SETI community has guidelines, but no global authority enforces them. Would we respond? Stay silent? Who gets to decide? What if the object isn't trying to talk, just observe? Then there's the issue of interpretation. What if the signal doesn't contain language, but math, chemistry, or unknown patterns? Our assumptions about communication may not apply. We may misread a warning as an invitation or dismiss a message because it looks like noise. Let's not forget the public. In the age of instant information, even a rumor of alien contact would spread worldwide in seconds. Panic, misinformation, and conspiracy theories would surge. Managing that, scientifically and socially, is something we've never rehearsed for. And what about the object itself? Suppose we detect something artificial at the edge of the solar system. Do we send a probe? Do we try to retrieve it? We may not be technologically ready to engage with what we find. Chasing a fast-moving object or studying a fragile relic might be beyond our current capability. Some scientists even argue we shouldn't be looking. The dark forest hypothesis, for example, suggests that intelligent civilizations stay silent because the universe is dangerous, full of watchers, not talkers. By sending signals, we might be exposing ourselves to unknown risks. Yet others say it's too late. Earth has been broadcasting radio waves for over a century. If someone's listening, they already know we're here. In that case, the real question isn't, are we ready to find something, but are we ready for something to find us? The deeper issue is humility. Much of our science assumes we're the reference point, our chemistry, our logic, our way of thinking. But truly alien contact might break those assumptions. We may need to build new tools, new science, and new ways of thinking just to begin understanding what we find. And even if we're not ready, discovery won't wait. The solar system's edge is filling with mysteries, and we're pushing closer every year. When the unexpected arrives, and it will, we won't have the luxury of preparation. We'll have only our curiosity, our fear, and our ability to adapt. Maybe readiness isn't a fixed state. Maybe it's the willingness to ask better questions, change our models, and rethink our place in the cosmos.
If that's the case, the real test isn't whether we're ready to find something, it's whether we're ready to be changed by it. Why have we explored so little of our cosmic backyard? We've landed rovers on Mars, sent probes to the gas giants, and photographed galaxies billions of light years away. But somehow, we've explored only a tiny fraction of our own solar system's edge. Why is our own backyard still mostly unmapped, unknown, and ignored? Part of the reason is distance. The Kuiper Belt, for example, starts at 30 AU, 30 times farther from the Sun than Earth. The Oort cloud might extend to 100,000 AU. Even traveling at Voyager speeds, it would take tens of thousands of years to cross it. We've barely scratched the surface. Another challenge is visibility. Objects that far out are cold, dark, and tiny. They reflect little sunlight and emit no heat. Even the biggest telescopes struggle to detect them unless they move in front of stars. It's not that they're rare, it's that they're practically invisible with current tools. There's also the funding problem. Space agencies prioritize missions that offer quick returns or compelling images. A probe to the outer solar system might take 20 years just to arrive. Politically and economically, that's hard to justify when Mars missions or lunar projects show results in months. Technology is a bottleneck too. Our current propulsion systems are slow by interstellar standards. We can reach Mars in months, but Pluto took New Horizons nearly a decade, and it flew by in hours. A mission to Sedna, Eris, or the Oort cloud would demand entirely new engineering. And yet, the secrets out there are enormous. The Kuiper Belt may contain thousands of dwarf planets. The Oort cloud may hold millions of icy bodies, some possibly from other star systems. We've detected only a handful. Most are unknown and could hold keys to understanding the solar system's formation. There's also the possibility of surprises, unseen planets, rogue objects, or artificial anomalies. These regions are gravitationally active, shaped by forces we still don't fully understand. Studying them could solve mysteries like the origin of long-period comets or the possible existence of Planet 9. Missions like Voyager and New Horizons have proven that deep space exploration is possible and valuable. The data they returned changed planetary science. But since New Horizons, no missions have been launched to go farther. There is still no confirmed follow-up to explore the true outer boundary. The good news? That may be changing. NASA, ESA, and private groups are proposing missions to explore interstellar space, Kuiper Belt objects, and even Oort cloud flybys. Concepts like nuclear electric propulsion or solar sails could cut travel time dramatically, but these are still in development. The bigger issue may be mindset. We've treated the solar system's edge as an afterthought, a place where things stop. But in truth, it's where things begin to get strange. It's the frontier of discovery, the unknown that's still within reach, but just barely. Exploring our cosmic backyard isn't just about science, it's about perspective. We need to understand what surrounds us before we look too far beyond. There may be more danger or wonder in the Oort cloud than in any distant galaxy. And one day, when humanity truly sets sail into the stars, the outer solar system will be our launch pad, our shield, and our last checkpoint. Understanding it isn't optional. It's the next chapter of our story, and we're late to start reading it. What might be waiting in the silent darkness beyond the sun? The further you go from the sun, the stranger space becomes. Light fades, temperature drops, the solar wind weakens and eventually stops. Beyond the heliopause lies a region we call interstellar space, a zone so vast, so cold and so faint that we've only begun to imagine what might exist there, and yet something might be waiting. This space is not empty. It's filled with a thin soup of neutral hydrogen, cosmic rays, and dust, the debris of ancient stars, supernovae, and collapsed systems. It's the environment between stars, a region so undisturbed that a small rock can travel for millions of years without hitting anything. But what if it's not completely quiet? We already know that the Voyager probes detected waves, subtle plasma oscillations that echo through this space. Those sounds, translated into audio, reveal a kind of hum beyond the sun. This isn't just poetic, it's physics. Something is vibrating out there, the galaxy itself breathing softly in the dark. Some of the particles entering this region appear to be accelerated, even without an obvious source. That suggests magnetic fields or unknown interactions might be taking place. These fields could be remnants of ancient collisions, rogue star winds, or even undiscovered astrophysical structures. There's also evidence of density fluctuations in the interstellar medium, places where dust or gas clumps together unexpectedly. These regions might hide massive objects that are invisible to telescopes, rogue planets, extinct stars, or even black dwarfs, cold remnants of sun-like stars that no longer shine. The silence out there may also hide artificial signals, ones that don't repeat, don't pulse, and don't follow our logic. We've barely monitored that space. Most of our telescopes face inward toward galaxies or exoplanets. Few listen carefully to the quiet zone just beyond the solar system. One idea is that probes from other civilizations might park themselves in this outer zone, waiting, listening, scanning. It's a perfect place for observation without interference. The sunlight is weak, radio chatter from Earth fades, but with the right equipment, a probe could easily detect and study us from this position. If there are structures or objects there, they would be extremely hard to see. Cold, dark, and distant, they wouldn't reflect light or emit heat. Only by observing the way they affect other things, like passing particles or weak gravitational tugs, could we even guess they exist. It's also possible that this region is filled with interstellar travelers, comets, icy asteroids, or even fragments of ancient planetary systems flung out during stellar formation. Some of these may be passing through our system now, looping silently in the void, never to be seen again. There are theories that strange phenomena, like unexplained dips in starlight or irregular orbits of distant objects, might be caused by something massive lurking just beyond what we can detect. A failed brown dwarf, a cluster of dark comets, or a relic of a time before the sun even existed. The darkness beyond the sun is not just space. It's a test of our limits, of what our instruments can detect, of what our minds are willing to consider, of how we define nothing. We once thought Pluto was the edge, then the Kuiper belt, then the Oort cloud. Now we realize there may be no clear edge at all. Whatever is waiting out there, natural or not, it exists beyond the warmth and control of our star. It's a place where the rules begin to change, where gravity stretches thin, and where even time seems slower. It's the last shadow before interstellar space begins, and it may hold the next great mystery of our existence.